and she's going to speak about the analysis of gravitational instantons.
All right, thank you very much. First of all, I'd like to thank the organizers for giving me this opportunity to speak here. It's a great honor. And so the topic today will be gravitational instantons. In some sense, it's again a bit far away from most of the topics for this conference. In the sense, it's coming from Kähler geometry and complex geometry. But my hope is that I'll talk about some of the analysis tools which might be interesting to some of you, and hopefully this will open some conversations. So my plan is the following, that I'm going to first talk about the background. So what are gravitational instantons? Maybe for some of you it's familiar and some of you it's a new topic. And then I'm going to talk about 3 projects that are related to this topic. The first one is in some sense it's closer to the minimal surface world. It's about the existence of some non-holomorphic minimal spheres in the gravitational instantons. And then the second project will be the main one, which is analysis we do for the so-called ALH space, ALH star space, which I'll talk about later. And we'll introduce the analysis tool to talk about the Fredholm theory and then what kind of applications we can get from this Fredholm theory. And the third project is another project about degeneration of those spaces. Okay, so let me start by talking about the basics. So what are gravitational instantons? Okay, so for some of us, Calabi-Yau manifolds in some sense is a standard object, that it's a Kähler manifold as with a special holonomy in SUN, and by Yau's theorem we know that there is a Ricci flat metric. So this is we're going to focus on real dimension 4. Okay, so by Calabi-Yau, this can be any 2n dimension, real 2n dimension. But for us, n will be 2, so real dimension 4. And in real dimension 4 case, the Calabi-Yau manifold has another structure, which is so-called hyperkähler structure. So it's not only Kähler, it's hyperkähler. By definition, this means that there's not only one complex structure which is special in the Kähler structure. Actually, there are 3 special ones, and they satisfy the so-called quaternion relations. So there are 3 I, j, k, and satisfy ij equal to k, jk equal to I, and ki equal to j. And moreover, in fact, if you have the 3 of them, then you can do linear combination of them, and you can actually get a whole sphere of complex structures. So you can rotate them. Okay, so and the reason why they have this hyperkähler structure for the holonomy reason is that when n equal to 2, so when I say n equal to 2, it's really a complex n here. So SU2 is actually equal to SP1 by an accident. So in this case, when we have this SPN special holonomy, you have the hyperkähler structure. So in particular, when we are in our work, in this talk, everything will be real dimension 4. Then every Calabi-Yau is also a hyperkähler manifold. And now, if we're talking about complex manifold, there are 2. I mean, there are 2 kinds. That the compact Calabi-Yau manifolds are characterized into 2 kinds. The first one is a torus, the complex flat torus, and then the other family of manifolds you can see are K3 surfaces. So you can say that we know a lot about them already, but you can also say that, especially for K3, a lot of them is unknown. For example, what does a metric look like? That for Yau's theorem, it's an implicit construction. You solve the Monge-Ampere equation, you get the metric, but we don't know what the metric looks like. So here motivates the study of a non-compact analog, which we'll see why it helps understand, say, the compact ones. So the non-compact analog are called gravitational instantons. I believe the name was given by Hawking, and it's remotely related to the fact that it's Ricci flat and it's Einstein. But other than that, I don't know how much is related to gravitation, for example. So this is the gravitational instantons. By definition, they are non-compact, complete, hyperkähler for manifolds. So basically, you remove the compactness and add completeness, and also require that the complete end has a good decay. And here we require that the curvature decays at L2. So it has some control at infinity. And by the way, I should also say that it was mentioned yesterday by the splitting theorem that because we are in the Ricci flat case, and then we only have one end, because otherwise you split out the line, and that's not interesting. Okay, so we only have one end, and this end is where things happen. Now, why do we study about those things? So there are several reasons. One of the main motivations is that those non-compact objects give you some information about the compact ones. So there has been a lot of gluing constructions of so-called bubbling analysis that you build those K3 surfaces, or K3 metrics from the gravitational instantons. Because when you have a family of K3 metrics and they degenerate, and then when you zoom back, you get those gravitational instantons. So it's like you're looking at what happens in the limit, and then when you come back to a little bit, you get the compact ones. Okay, so this gives us explicit expression of metrics of K3, at least when it's near degeneration. And gravitational instantons are also interesting by itself because it's conjectured that all of them can be realized as some solutions to gauge as a moduli space of gauge equation solutions. So there's a large interest in the Higgs bundle vortices and those things in that people want to construct solutions and then realize them as gravitational instantons. And then there's also interesting, at least for our analysts, that it has very special geometric structures at the end and somehow provides a rich family to study and gives us opens up new analysis tools. Okay, so now let me talk about the end. So that's so as I said, that each gravitational instanton will have one end, and this end is determined, and the infinity structure determines what kind of gravitational you are. So there are 6 types. So the first one is called ALE, which stands for asymptotic locally Euclidean. And in terms of volume growth, it's like a piece of R4, or it can be modeled by a finite group. Okay. Now the next one is so-called ALF, so it stands for asymptotic locally flat. And this is our volume growth R3. So you can view it as a cone over a circle. Now, the next one is called ALG and ALH. Unfortunately, G and H does not stand for anything. They just stand for E and F. Okay, so EFGH. Okay. So here, and by volume growth, ALG and ALH, they are volume growth 2 and 1. So they're slowly getting smaller and smaller. Now it turns out there are 2 more types. There is called ALG star and ALH star. They are so-called like special ones. And they are named, again, G and H does not stand for anything, and star stands for they're special. And the reason they're named those 2 is because if you look at the volume growth, they're kind of between ALG and ALH. Okay, so you might want to say, okay, well, are there any more? Why are there only those six? And there is so there are big theorems by Minerva. Oh, okay, sorry, I see. I should go. Okay, by Minerva, Chen, and Chen, and recent work of Sun and Zhang, they show that if you give a gravitational instanton, then it's one of the 6 types. There's nothing more arising from it. So that's why it's in some sense our choices are limited. But of course, within each type, there's a lot of stories. So in our talk today, I'm going to talk about more or less 3 types, mostly focusing on ALH star, and then I'm also going to mention ALH and ALF. So one of the things that we care about is how they are related. So the folklore conjecture is that all of them are related. They're going to fit into this huge moduli space. And the reason is because physicists believe that they are all realized as some kind of moduli space gauge equations, and those gauge equations are related to each other. So they can often merge one from to another. So for example, one of the works by Offray was showing that if you start with an ALF, you can get to ALE. By opening up the circle bigger and bigger and bigger, eventually it gets to from a cone to R4. And there's also a work in progress joined with Yu Shenlin and Song Sararian, and I'll talk about that in the end, about relating ALH star, ALH, and ALG and ALG star. Okay, now let me talk a little bit about math. So what are the ends? And for most of the gravitational instantons, the lucky thing is that the ends is pretty explicit. So it's constructed by something called Gibbons-Hawking ansatz. And the idea is that if the end has an S1 symmetry, then you can realize it. So I think now it's my time to use a board. So you start with a 3-dimensional manifold, which I call U. Okay, so this U is a flat manifold, and you have some choices. And then there is going to be a circle bundle over it. And this forms a 4-dimensional manifold. So it's M4 fibers over U3. And on this M4, I'm going to put a metric. But in addition, before that, I'll need to have another ingredient, which is one harmonic function. on U. And this harmonic function is not arbitrary, it has some kind of quantization condition here. It needs to have this homology condition. But other than that, you're free to choose whichever V you want. And now, once you have this V, we're going to assemble the metric in the following form. Okay, I think I just gave up the clicker. We'll have two parts. The first part is a flat part. So more or less, you're going to put the flat part and the circle part together, but they're weighted. And the weights are exactly given by the harmonic function. So the first part has a V and the second part has a V inverse. Okay, so it might still look a bit abstract. I'm going to start with examples. So if we start with U, so the base 3 manifold to be R3, it's certainly a flat manifold. And take V to be 1 over 2R, which has singularity at the center, but other than that, it's a very nice harmonic function. And then if we take a hop of vibration at infinity and goes into for R4 over R3, then you can actually just assemble the metric in the usual way. This is just a flat metric on R4. So this is a typical example of an ALE metric. Now, the second one is similar, except I'll modify the harmonic function a little bit just by adding a constant. Once you add a constant, the volume growth at infinity actually decreases to R cubed instead of R4s. And then the same hop of vibration will give you another famous space called Taub-Knot space. And this is an ALF space. Now, if we change our base manifold a bit to T2 cross R, which is still a flat manifold, just use the usual product metric on T2 cross R, and then use an even simpler harmonic function, which is a constant. Then if you plug in there, well, that's a simple thing to check that you'll get T3 cross R because there's another circle there. So in terms of volume growth and everything, you can check that this is a typical metric in ALH family. Okay, so those ones are somewhat well-known and understood. And there's another one here. It's similar to the previous example. I'm going to use the same base manifold, which is a T2 cross R here. And using vibration, which I haven't said what kind of vibration it is, but I'm going to use the vibration and I use a V, which is a harmonic function that has a variable in it, Z, which is there's an R direction. So I'll take this R to be the Z here. And then if I plug in there, there's something called a Calabi model. And this is a typical ALH star metric. Okay. And I put a B there. And for now, it doesn't matter. It's an integer, and that's going to happen later for some kind of degree. Okay. So before I talk about the ALH star in more detail, let me just say a bit of where things happen. Well, one of the main reasons why we care about this is that they arise as bubbles in the degeneration of compact Calabi-Yau surfaces. So it has a rich literature starting from about 30 years ago. That started from Gross-Wilson's work. There's Foscolo and Chen, Heinsohn, Vyakovsky, Zhang, and collaborators. And more or less the theme is that you use one of the gravitational instantons as bubbles, and then you construct compact K3 metrics. And now, depending on what kind of gravitational instantons you use, the degeneration objects can be different dimension. So for example, the recent work of Heinsohn, Vyakovsky, Zhang is that you use ALH star and constructed a family of K3 that degenerates into a segment, into one dimension. And on the other hand, for example, the work of Foscolo was using ELF to degenerate into two-dimensional torus. So there are all kinds of degenerations, and more or less all the gravitational instantons can be realized as bubbles. And there's also other work in related subjects. For example, Odaka Oshima has this algebraic geometry version of this degeneration. And then there's also two work I want to mention. One is Tristan Azouk's work on Kähler-Einstein metrics, which is also using gravitational instantons as bubbles. And then there's also recent work of Bera, Isfahani, and Yang Li that uses gravitational instantons to get information about Calabi-Yau manifolds, again, as using them as bubbles. So as I said, that the main reason is that K3 surfaces are really too mysterious, that metrically we can't get a hold of it. So that's why we want to use a more explicit metric, at least to understand what happens when K3 are a nearly degeneration. And so one of the things we did recently was to show that you can actually find some special objects in K3 surfaces. And those objects are non-holomorphic minimal spheres. So when I say the minimal, they're just in usual way that they're minimal, and they're actually stable minimal. They're absolute minimal. And but they're non-holomorphic in the sense that if you take any of the compatible structures of the K3 surfaces, remember there it's hyperkähler, so you have a lot of complex structures to choose from, but none of them is compatible with this minimal sphere. So it's kind of like the opposite version of the Wirtinger, that if you know that so if you are holomorphic, then you're minimal, but not the other way. So there's a one of the motivations about this work was, well, first of all, finding minimal spheres is always kind of interesting. And another motivation is something from physics called weak gravity conjecture, that you can find so-called non-BPS particles in Calabi-Yau manifolds, and those non-holomorphic ones corresponding to non-BPS particles. Okay, so let me say a little bit about this work. So this has a history, and the main one of the first works on this direction was Mikhailov and Wolfson. They showed that you can find such objects in K3 and in somewhat non-explicit ways. And there's also more recent work by Taiwan, Lotte Oliveira, and Fons Coller-Treca in finding all kinds of non-holomorphic minimal submanifolds. And what I want to say here is that it's related to gravitational instantons. The reason is that, in fact, we can't directly find this minimal sphere there. And what we did was to find a bubble, which is an ALF space. So it's kind of related to this Taubner space that I mentioned, but it's it's glued from a multi-Taubner space. And then it's glued to a special manifold, so-called Atiyah-Hitchin manifold. And this one is from monopole space, and is constructed by Atiyah-Hitchin, and there is an explicit construction to find one special sphere there. And then what we need to do is to glue this into a bigger space, and then glue this bigger space into K3. Okay, so more or less the idea is that if you have bubbles, then you can get information about the compact ones. Okay, so right, that's what I just said. So some kind of gluing construction, and there some analysis is needed, but I'll skip that for now. And one thing I do want to mention is about the stability and instability. That right, let me go here. So the recent work of Lorenzo Fonscolo and Federico Trinca, they actually constructed something again in K3, and inside basically the same space, but they got some other minimal spheres which are not stable, which is very surprising, but in the same homology class. So there's one question of what happens to those two. Do they merge at some point? Do they both disappear in the middle and then they somehow branch into two sides? So this is some question that I would like to have it answered by somebody working in minimal surface world, that somehow some kind of strange behavior when you go into interior, and then you get the branch. I'm not sure if it's branching, that something becomes stable and something becomes unstable. And now there are also other questions related. In particular, so what happens when you go into the interior? Do they really disappear, and do they become a lot more, and then or something like that happens? Okay, so this is the first projects I want to mention. Let's give an idea of why we care about those gravitational instantons. And now let me go to a different type of gravitational instantons and talk about the analysis there. So this is a project joined with Rafe Matil about an ALH star metric, which I'll talk about more in detail what they look like. And the main theorem has a few components. So the main analysis results we get is that you can get a mapping property of the Laplacian, and also similar elliptic operator like Dirac operators as such. And the point is that you can get a Fredholm property, and you know exactly how they map. And then once you have that, you can get the L2 harmonic form theory, and also get the asymptotic expansion. And moreover, one can get a perturbation theory of such metrics. So this is, again, ties into the theme of understanding the moduli space of gravitational instantons, that if you start with one, can you perturb nearby? So in some sense, it's similar to if you have a K3 surface, can you perturb nearby and see what else are there? People kind of know what they are, well, but not explicitly. And here the point is that, at least for gravitational instantons, we know explicitly what the perturbation you need is, and we know exactly how to compute it. And in particular, you can identify the components, or you can identify the tangent space, which direction you can go to get where. Okay. But before that, let me at least say what ALH star is. Okay, so recall that we have the Gibbons-Hawking ansatz here, and I wrote down the Gibbons-Hawking ansatz earlier. I'll just rewrite here with simpler terms by taking off all the constants. So if you do the y1, y2 on the torus fiber, and z to be the variable on R, and then take theta as one fiber, then this is a metric. Okay, so this metric itself looks pretty harmless. That you're just putting together two parts and write it down like that. And you can keep it like that. And in my convention, I would switch z to be 1 over x. In some sense, I don't like z going to infinity. I want something to go to 0 instead. This is just a convention. You don't have to do that. Now, if I do that, I can bring this into a format like that. Okay. Now let's see a little bit what this metric really is behaving. This has a doubly warped behavior. That first of all, there is this dx. This is x is going to 0 now, so this is like the direction going to infinity or going to the boundary. And this has a dx over x to 5, which is a pain because you can see this number 5 is not a usual component. But there are also two other components here. That this is dy1, dy2. Remember, this is torus direction, and torus direction, the metric has an x component, 1 over x there. So x is going to 0. And here, torus is a blue one, okay? So the blue one, when you're going to the boundary, the torus is expanding because you have 1 over x. So that's why the metric, the torus direction is getting bigger and bigger. And on the other hand, I have another factor x, which is in front of the circle. So here, circle is a red direction. And when x is going to 0 or going to the boundary, the circle is shrinking. So yeah. Why? Right. If you just want to see this behavior, this is the original Gibbons-Hawking ansatz is perfectly fine. There's no problem. You can just see that. For the choice of changing into a 1 over x is for later when we do analysis. This is again, it's a choice. It's a preference. Okay. It's not. In some sense, it might not be even the standard choice here, but it's convenient for us. So yeah, if you just want to see this kind of doubly warped behavior, the first form is perfectly fine. Yeah. So as you can see that, so this is a double fibration where some fibers are expanding, some fibers are shrinking, and they're all shrinking and they're all having this weird components, x to 5th, 1 over x, and x. That's where you can see the pain of analysis is. Okay. So before that, let me just say a little bit of history that where this thing come from. So this was first constructed. Or this metric itself is this model is called Calabi ansatz, which was constructed by Calabi, and then later the first appearance was in Tian Yao's paper on constructing non-compact complete hyperkähler metrics or Calabi metric. This is one of the models they use. They showed that you can construct a metric that's asymptotic to this at the infinity. And later, a more refined analysis was done by Hein in his thesis. And I should say that there's another way to do this complex version using the complex structure to write it, but I'll skip that. And there's a lot of generalization in this. One thing I want to mention is that there's a recent work by Yifan Chen who generalizes to higher dimensional Tian Yao metrics. So this is, again, it's a kind of double vibration, but you can generalize the higher dimension. And there's in some sense, more weird behaviors happen, but I'm not going to talk about it. And there's some joint work with Yifan Chen to understand more where the analysis there is. So in short, there are more things that can happen in higher dimension. Okay. And now, so ALH star was constructed by Tian Yao, and now later it became interesting because it appears in all kinds of places. So the first places that we learned about it was from this Hein, Sun, Vyakovsky, and Zhang's paper. They use it to, as I mentioned before, you have a family of K3 surfaces and you collapse, and then they're going to degenerate to a segment. And those are the bubbles on the end. And then there's also recent work by Collins, Jacob Lin. They have this series of papers constructing mirror pairs in SYZ symmetry. And it turns out that Tian Yao metric can be one end of this, one side of the pair. And the other side of the pair is so-called this generalized semi-flat metrics. And then basically they both have torus vibrations, and if you rotate one of them, you get the other side. So the Tian metric has a natural is a natural candidate for this kind of SYZ symmetry. And then related to this SYZ symmetry story, there's also on the Torelli theorem and weak del Pezzo surface theorem a story, which is more algebraic geometry. So I'll skip that. And more ALH star appeared in recent work by Picard and Ganassia. They use it to construct a family of conic Kähler-Einstein metrics, and they degenerate. And in the end, the Tian metrics appear as a limit. And then there's the earlier appearance of ALH star in physics was by Cherkis, that he constructed moduli spaces for monopole equations. But it's not the usual monopole, that if you do the usual one, you get a Tia-Hitchin manifold. That if you have some kind of prescribed boundary conditions, then you can actually get the ALH star as a moduli space. Okay, so in short, it turns out that they are in a lot of places, even though the metric looks pretty weird. Okay. So, so one of our motivation was to understand the mapping property of the operator. So you can imagine that basically, well, there's only one or really two Dirac operator and Laplace operators are usually useful for this kind of geometric construction. And in particular, in the gluing construction, one of the keys was to study the Laplace operators. So this mapping property, and at least the Liouville theorem, was known earlier by Heinz and Vierzchowski Zhang, Sun Zhang, and also earlier work by Caron. But we did get questions from the Heinz and Vierzchowski Zhang team. They said we cannot get a Fredholm theory. Maybe your tools can help. So that's where we came in, and it turns out that well, we can do it. And also Fredholm theory is not only useful as having a mapping property. You can use it to do other things. So later it turns out we can do Hodge theory and deformation theory on that. And the reason we can do that is that, so this is one of the themes in geometric microlocal analysis, that you study the singularity structure and understand what kind of analysis tools can be developed, and then you get the mapping properties. And this one, this ALH star metric, even though it looks weird, but if you suit it up a little bit and change it a little bit, it fits into one of the singularity structures people already studied. And it even applies to higher dimensional cases that I mentioned earlier. Okay, so, well, let me say a little bit about the Laplace operator here. That so the first thing I want to mention is that you can compute it explicitly. That at least for the model, that's a great thing about this whole thing, that you can just write out everything in local coordinates. Now, if you write in local coordinates, again, that those weird components is going to happen here. That's this x fifths and x inverse. And now you can ignore the lower terms. Those are all lower in terms of the mapping property. And then if you multiply an x, we get three powers: x to the 6, x squared, and x 0. So those are not standard powers. If you think about the usual okay, I don't know if it's called usual, the more standard AL, the fiber boundary of cusp metrics, those have different powers. The difference of 620 is not something that we have seen before. So it turns out that there is a name there. It was studied before, and it was an example studied by Gries and Hunsaker earlier. They call it A structure. So this A really does not stand for a word. It stands for a vector. That they study some kind of double vibration, that you can have different powers when you go into infinity. When this fiber will shrink in different powers. So they study a more general structure. But this A stands for, a vector stands for the different weights when you go into infinity. And this A cannot be arbitrary, has some constraints. And luckily, this one that we're studying here fits into the type. Okay, so. And there's similar structures if you change the different weights, and you get the fiber boundary or fiber cusp structures, which has appeared in other gravitational instantons as well. Okay, so let me just say that here, what one needs to do is to look at the three parts separately. And if you decompose it by doing the following, which is start by taking everything in, meaning that I'll take the S1 direction and T2 direction, and both of them are not harmonic. then what happens is that I'll get the first one, which is so-called a fully elliptic A operator, which has been studied before. And it just means that you have all three parts. Now, the second part is that if I take out this d theta part, meaning that I'll project into space where d theta part is 0, then I'll get a vector, operator that has both x6 and x2, and this is so-called a cusp operator with a weight. And the last one is if I take off both of the dy direction and d theta direction, which you might think it's silly, but it's not. It turns out the most analysis is actually on this part, or in some sense, it's so-called a B operator, which has only the x direction. So for some of you, if you worked on some of the geometric problems, what people do is do separation variables. At least for this particular problem, you can do that. And if you do separation of variables and do the mapping analysis, you realize that a lot of things will happen when you have the zero mode or do Fourier decomposition. That most of the complicated things are actually in the zero Fourier mode. And this exactly reflects to the case that when you remove this dy and d theta, when you only have this dx part, there's some kind of polynomial behavior. On the other hand, if you have a non-zero Fourier mode, you usually have some exponential decay, and then that's usually good. And then here there are two parts that take care of that. And in fact, it corresponds to that if you have those two parts, you have two kinds of exponential decay, but they are both nice, so we don't care about it. Okay, so let me say a little bit about this, what we're doing. Okay, so this is again the 10 minutes of, 5 minutes of lecture geometric analysis that nobody asked for. That I'm going to say a little bit about what we do here. That in order to get the Fredholm or mapping properties, what we usually do is you find the inverse for the Laplacian. Now, how do we get the inverse? You can't directly invert it. That if you have a compact space with a usual smooth Laplacian, you can do it by Fourier transform. And then you do it on the Fourier side, you just directly divide it by the symbol, more or less. And this, you can kind of do that, except this Laplacian is singular. In a lot of places, it's when you divide it, you'll get a lot of singularities. So this is where that you dive deep into this method of Fourier transform, and then see that what happens is that we need to find the Schwarz kernel of the inverse and the Laplacian. And it's I'll write down an example in a moment, and then construct and write down the Schwarz kernel explicitly. Now, I can't do explicitly for this Laplacian because it's too complicated. So what I'm going to do is I'm going to do a very simple example just to show you what usually this means. And to do that, I'm going to use the simplest one-dimensional manifold with boundary, which is a line, a segment, 0, 1. And I'm going to take the operator to be x times 1 minus x d by dx plus c. Okay, c is just a constant. So here, x is just a variable in 0, 1. Okay, so you might think, okay, this is not the first differential operator you would think of when you're on the line. Indeed, you're not. But if I choose a different variable, say if I take s to be the log of x over 1 minus x, then you'll see that this transform is going to expand 0, 1 to be from minus infinity to infinity. And this operator, if you use the new variables, you'll see that this PC is actually just equal to d by ds plus c on R. Okay, so this is just another way to write it. Again, it goes to the theme of bringing infinity to finite part, that I'm going to bring infinity back to 0 and 1 so that I can analyze it easier. Okay, so it's just this operator, and I want to know the mapping property. And again, for this one itself, you can explicitly write it down. And what we're going to do is I'm going to construct the inverse. So what do I mean by constructing inverse? Meaning that if I write PC u equal to f, then I can write this u to be equal to QC applied to f. Okay, so this is just writing out explicitly the inverse operator. And for this one, well, it's just the first order ODE. You can do integration directly. And now I can write it out explicitly. So QCFX can be written as the following. So I'll write out explicitly first, then I'll explain. So it's integration from 1 to x of x over 1 minus x to the c's power, and then x prime over 1 minus x prime to the minus c power, and f x prime dx prime over x prime times 1 minus x prime. Okay. So there are two variables here. That's the usual way. That's the usual Schwartz kernel integration kernel that you apply to an f and get out a function of x. And the way to do it is that you integrate fx, fx prime against integration kernel, integrate out the x prime variable, then you get a function of x. Okay. Now for this one, if you're bored for the next 25 minutes, you can try to do it yourself. It's fairly straightforward, especially if you flip back to this d by ds coordinates and then do change of variables. Then you'll see that this is exactly the formula you should get as the exact inverse. Okay. Now for this one, well, I can write it in a slightly different way. I'm going to write it as integration from 0, 1 of a kernel, which I'll call it k, x prime, integrating against fx prime. And then there is a volume form that I'll write in this way, just because this is better suited for this operator. And now for this one, I think I should wrote it slightly bigger than I thought I should be. I'm going to erase this part, and I'm going to take out the kxx prime. So this is the main part, as usual, that for a differential or pseudo-differential operator, this is a Schwartz kernel, and that's where all the analysis is inside here. Okay, so well, this is just kxx prime can be written as minus x to the c's power minus over 1 minus x to the c times 1 minus x prime to the c power and x prime to the c power. And then there is a Heaviside function, x minus x prime. Okay. So the reason why there's a Heaviside function is because here we have 1 to x, and here it's 0 to 1. So I need to cut it off. Okay. So this again, just well, write out explicitly from here to here, you get this k. Okay. Now, that in general, the idea is that if you know everything about this k, then you know everything about how this mapping property of QC works. And again, the idea is that you want to know which space you can map from which space. Right? So now let's understand this kx prime a little bit. Again, this one is very explicit. And as I said here, that they live on the double space because they have two variables. That so even in the higher dimensional case, it's the same. That you have one variable that's a dummy variable that's going to be integrated out, and one variable that's the original space. Okay, so here then my original space is actually 0, 1 cross 0, 1, so it's a square. Okay, now let's look at this this kernel here, and let's see where are the singularities. So there are two types of singularities. The first type is those 1 minus x prime, 1 minus x and x prime, and x and 1 minus x prime. And the reason is that c doesn't have to be positive. If c is negative, then the other side is. So in short, we have those, well, the four sides here, they are singular. Okay, this has some polynomial singularities there. Now, they're not the only singularities. There's another type of singularity, which is here on this Heaviside function. You have a delta type singularity, which is on the diagonal. So x equal to x prime, that's a singularity. Now, as you can see that this side is fine, this side is fine, this side is fine, and in fact, there's some analysis that can be explained explicitly. However, we have those two corners. They're a bit of a trouble because there are two types of singularities coming together. And in analysis, they represent two types of things. In general, that analysis of the singularity on the diagonal or of the Schwartz kernel stands for the differential singularity. This is like a regularity singularity. And on the singularity on the two sides stands for the decay singularity or the decay estimate. Now, the problem is that they two are coupled together here. So one way to deal with this problem is that we want to separate singularities so that the analysis can be done separately. And this is one of the themes for geometric microlocal analysis, that you introduce a resolution here at the two sides where the singularities meet. So we introduce a new space, which is like that. That so that my singularities now are going to be separated. So there's a two-side polynomial singularity, and there's a diagonal singularity. And they no longer meet. And in particular, the analysis of the regularity, or you can say regularity estimate, and the decay estimate can be done separately. And so this has two ways to think about it. One way is just to think about it as geometrically as a blow up. So for some of you might be more familiar. It's you're just blowing up a singularity in a space. And another way to think about it is that we're just introducing some new polar coordinates here. If you introduce polar coordinates here, then this and this can be written separately. Okay. So that's more or less that's a gist. And the point is that once you have this, then I mean, this k xx prime, at least in this example, is fairly straightforward. We don't really need to do this to analyze it. But for more complicated spaces, if we are in this new space here, using those new coordinates, the inverse is much easier to construct because you can construct the inverse here, which is by inverting the symbol, and then you can construct the inverse here, which is by looking at the power behavior. Okay, so this is more or less the 5 minutes that of geometric bicolor analysis that I want to talk about. And this is more or less the gist of this. Of course, for those problems that we're dealing with, it's more complicated. It's not just this one level. It turns out there are 3 levels. You need to introduce different coordinates in different levels to represent this x6, x squared, and x0, more or less. And I should say that the most complicated thing is actually in the B level, which is just this level. It's just one variable. However, that just like if you have seen, well, if you know d by ds is not a very good operator on R. It's not Fredholm if just the mapping from H1 to L2, that you actually need to add some weight. So similarly, that for those problems that depending on what kind of operators you have, you'll need to add some weights and add some singularity at infinity to deal with the idea, to deal with the mapping property. Okay, so now so the basic idea is that you get this M2, which is more complicated. Now it's 4-dimensional by 4-dimensional, so 8-dimensional space, and then introduce all the correct coordinates and construct the inverse on the double space, writing out this K, at least piecing them together, and then get inverse. So with that, now the short version of that, you can get it parametric. It's not exactly an inverse at this point, but it's inverted enough in the sense that error is compact. Now, and once we have that, we know that you can get a Fredholm property. Now, but the price to pay is that your space is no longer the original space. Your space is here. So the Sobolev space or the holder space you'll be working with is no longer the usual Sobolev space or holder space. You'll need to add singularity to counting the fact that we're adding new coordinates here, and we'll also need to add in weight because d by ds is no longer Fredholm on the usual space. You'll need to add some weights. So this so-called avoiding the indicial roots. And but more or less, the idea is that you can just construct the inverse. And with that, okay, I should skip that part. So let me just say that the first thing one can do is about L2 cohomology. I'll skip that. And it's somewhat standard. And the point is that once you have a metric singularity, the behavior of cohomology is slightly different from the usual cohomology. And one can use the L2 cohomology to detect the infinity. So I'll skip that part. And there's a way to do it here by a somewhat standard application. And the second application is that one can get the asymptotic expansion of the metric. And again, in this case, it's not too hard because we already know what the Laplacian maps it looks like. So we're just solving a complex non-general pair equation, but this time it's within small perturbations, so it's easier to deal with. Now, I'd like to talk about the third, or you can say the major motivation for understanding the Laplacian, which is understanding the perturbation. So as I said before, that there's already kind of algebraic geometry description of the ALH star. That it turns out that you can compactify it to elliptic surfaces, and there's some kind of Torelli type theorem to describe it. Now, our approach is that suppose I do not know anything about algebraic geometry, which I don't. So I just want to understand it as differential geometry. That if I just have this hyperkähler metric and I want to perturb nearby, what kind of other hyperkähler structures can I get? So the basic setup here is called hyperkähler triples, which was initiated by Donaldson and then later was used in many places. So the idea is that we're going to solve for the hyperkähler structure by solving 3 symplectic forms, which are the 3 forms that's in the 3 Kähler structures. And then they need to satisfy this condition here. This omega wedge omega j has to be delta ij, more or less. And if you know that they satisfy the three equations, then you actually get hyperkähler triple. Okay, so which is quite strong, and there's a reason why you can get from this kind of looking like algebra equations to get the Ricci flat metric, but there's a proof there. Okay, so all we need to do is to solve this three quadratic equations, and turns out that if you linearize it after all the gauge, you'll get 12 copies of scalar Laplace operators. So, which is great news because we know what Laplace operators behave like. That's so. I mean, it's not the end of the story. I'll say a little bit of why it's not still non-trivial. But in the end, what we get is that the local perturbation for a hyperkähler structure for this ALH star comes from two pieces. So it's kind of expected in some sense that you can perturb the interior by fixing the end, and the interior has you have some freedom to perturb in the interior, which is down by this anti-self-dual to harmonic forms. And there is and even for compact hyperkähler structure, you have that piece. And depending on how much topology you have inside, you'll know how much you can do. Now, there's another piece, which is at infinity. So you can perturb the end structure. And here, the end structure has, we want to have the bounded constructions or bounded perturbations. So in some sense, it's like you're still keeping the structure at infinity, but you can perturb it. Recall that the end has a circle, has a torus, and has a thing that's going in. Now there are two pieces you can perturb. One is you can perturb the torus by changing the complex module, which is 2-dimension. And then you can change the relative scale of the circle with the torus. That's another variable, and that's it. It turns out that there's only 3-dimensional freedom at infinity, and then whatever topology you have in the interior. Okay, so well, okay, I won't say too much about it, but I just I want to mention that it's something quite interesting. Turns out that there's some kind of algebra there, that some kind of linear algebra there, that one can in the end the perturbation at end goes into a 3x3 matrix and 2x3 matrix. Well, it's a 3x3, but with a line being 0. So there are 15 variables with 6 equations, and then with 3 dimension of gauge. So in the end, you end up with 6 different variables in some sense. So this equation, in some sense, this is complete algebraic equations that just have 15 numbers, you can say, and with 9 equations. Now you can imagine that once you take it out, you get 6 freedom. And if you just look at this equation, and the requirement is the AAT minus BBT equal to identity. Okay, that's already there. And then you'll see that whatever B I put in here, I'll be able to solve out an A up to gauge. Okay, so in theory, I should have 6 dimensions of freedom. But geometrically, I only have 3-dimensional freedom. And that's where the particular geometry comes in. It turns out that the 6 is not really 6. The 6 is 3 plus 3. And 3 and 3 should be identified because there's an extra hyperkähler identification which was discovered by other people, that there is this mirror symmetry comes in, that you have the Calabi model and you have the semi-flat metric model. And those two represent the 3 and 3 here. But they should be identified because they really represent the same hyperkähler structure. So that's where things were complicated and took us a while to figure out. But the point is that in the end, you got the dimension, correct? And that matches everything with the algebraic geometry side. Okay, so, well, maybe I'll have another 5 minutes to talk about the last thing, which is how once you get the moduli space, or at least a local deformation, that you will want to know what happens when you go to the boundary of the moduli space. And that's where the degeneration comes in. That turns out that the moduli space is non-compact, as you expect. Most moduli spaces are non-compact. And so there are several ways to see how it's non-compact. We still don't know everything about it, but at least we know some information about how you can approach the boundary. So there are, just like K3, the moduli space of K3 surface is still a large unknown. That you have the Torelli theorem, you have this fixed dimension, 57-dimensional space, and we know some directions where it goes, but there are a lot of things we don't know. And there is actually the theoretical picture of the conjectural picture of the moduli space compactification has this very weird shape. And similar for gravitational instantons. We don't know everything, but we know some directions. So it turns out that at least one of the directions is that a gravitational instanton can merge from one place to another place. And so one example, as I mentioned earlier, is by earlier work by Ovray. He showed that if you start with an ALF, which is a cone over a circle, and then you open the circle, eventually the circle goes to, the radius of the circle goes to infinity, you end up with R4. So that's more a model of ALF to ALE. And what we did was that, joined with Yu Shenling and Saunders Arroyan, is that we constructed another type of degeneration, which is starting from ALH. Then you can go through different types of ALH star until you get to the end. So this is more or less a bubble tree structure. That so there are those numbers, but because there's a degree, but you don't need to think about it too much. That the intuition is that inside those gravitational instantons, there are monopoles. You can see them as singularities, and the number b stands for the number of monopoles. And when b equal to 0, there are 9 monopoles. And when b equal to 0, 9 monopoles, and ALH star 0 can be viewed as a version of ALH. And when you take one monopole and split off into infinity, the structure changes, and the end structure changes, and the type changes. And now, so I started with 9 monopoles. I can split off one by one, or you can split off a few at the same time. Doesn't matter. In the end, that when one monopole disappears, the topology gets a bit simpler, and then more monopole disappears, the topology gets even simpler. If you push out all 9 monopoles to infinity, there's nothing in the interior. Topology is extremely simple in the interior, and you get to this ALH star 9, which is more or less you only have the end, and there's nothing in the interior. Okay, so that's a picture. And there is a version of this in algebraic geometry, which is done earlier by Cherkis in his physics paper, that you can get this kind of bubble tree structure from the Delpetto surface point of view. And we can also use rational elliptic surfaces to do that. But I just want to mention this one picture that I said earlier, that the point is that an ALH star b minus 1 can be viewed as a neck plus an ALH star b, where the monopole is here. And then the degeneration happens when you make this whole thing longer and thinner, and you put this neck extremely long, and then you push this monopole to infinity. Now you can imagine that once the monopole goes to infinity, the right part just disappears in the Gromov-Hausdorff convergence sense, and then we end up with this left part. So this is how the degeneration happens from a lower ALH star to a higher ALH star. And when b equal to 9, this is the best you can do, because there's nothing else to split off. Okay, so there is a version of that by using the case-free version, but I'll skip that. So I just want to mention, so this is one part of our project, was to show that you can have this Gromov-Hausdorff convergence of limit between different types. And of course, the actual construction was using gluing by kind of inverting the construction. You glue back the neck with a cap on the left, and then you glue back a smaller one. And then the analysis there is similar to what we had before, which is using the singular space, but you need to have a better convergence, better control of convergence. And there is a similar, we can also do similar things for ALG and ALG star. And in fact, it turns out we realized that we can also do it between the different types. So the ALG, ALG star, ALH, and ALH star, they're all kind of related in some way. You can view them as like apartments. You have lower level is ALH and ALH star, and ALG and ALG star is on the higher level. You can go from the same level from one room to another room. You can also use the stairs to go from the base to the top. So they're all kind of related in some kind of degeneration. And so this can be viewed as a compactification, but it's only partial, in the sense that we don't really know if that's everything. That just like in K3 moduli space, there are all kinds of weird compactifications. It's hard to realize that in the gravitational instanton world, it's also unclear what is a correct compactification or complete compactification at this point. Okay, so this is just one of the things we did. All right, so that's all I want to say, and thank you very much for your attention.
for this interesting talk. Other questions?
Thank you very much. Can you come back a little bit to the result about the parametrics?
Parametrics, yeah.
And can you tell me a little bit more about the geometric construction of a blown-up space? So I expect that you do blow-up of blow-ups.
Right. So here, okay, I'm not going to really say that the blow-up because that's going to freak out everybody else. That it's going to yeah. So the basic idea is that in this case you have the first level is more or less the corner here like that. So it's so-called a B blow-up. So you resolve the first level of a singularity. But then, of course, there's more because we have the cusp singularity and A singularity. So the correct picture in some sense is like you have other dimensions because we have 8 dimensions here. And then what you need to do is do another level blow up here like that. And then blow up another corner here. Okay. So there are 3 levels of blow up, in some sense, introducing 3 types of polar coordinates
to
account for the
x0, x square, x6. So
more or less, that's right. Your goal is eventually this x cubed dx and x dy and d theta is going to be bring into new variables, and they're going to become dx, dy, and d theta. I'm going to call them different variables. Just under the new coordinates, this is your Laplacian becomes usual our Laplacian on R4.
Okay, thank you very much.
There was another one.
So I have a question about, so you mentioned there's a Calabi ansatz and then you have a Tianyao matrix, right?
Yeah.
So I wonder if the Calabi ansatz is like just one particular n type, or is actually a family of different n structures, and then for each one you can construct the Tianyao matrix. And more generally, I wonder, is this like the moduli space of AL H or AL H star?
Yeah.
So is that the moduli space, is it actually has a like a Banach manifold structure? So it's like you have deformation.
Right. So if we think about the interior or compact part of the moduli space of AOH star, indeed that it's all one part is the Calabi ansatz. And when we talk about Calabi ansatz, really you can think about it in the real version. It's the Gibbons-Hawking ansatz that I mentioned earlier. It's a circle over torus over line. And then all the freedom you have is that you can vary the torus and you can vary the relative scale. And that's all you have about the Calabi ansatz. And I mean, there is a discrete variable, which is how you can, there is a circle bundle degree. There's a B there, but this is a discrete variable. So locally you don't vary that. So and then it's only 3 dimension for the Calabi ansatz, and that's it. At least in the 4-dimensional case. Then the moduli space in the compact part, you have the boundary, you have the 3 variables, and then but you also have the interior topology. You can vary the interior topology to account for the hyperkähler structure change in the interior by fixing the end. So that's the moduli space, at least if you don't think about degeneration. And for higher dimensional cases, that there is also a Calabi ansatz, which is you choose, instead of having this torus, you have a flat higher dimensional complex manifold. And then there, of course, there's more dimension, there's more freedom. And it's also very unclear whether we have the moduli space, because by Yifan Chen's result that unlike Tianyao's result, once you have the Calabi ansatz, your actual Tianyao metrics is exponentially close to that Calabi ansatz in the end. That in the higher dimensional case, you only have polynomial close, and you do not have uniqueness if you only have the uniqueness question is much more complicated. So it's unclear what's the dimension count there.
So the uniqueness, you mean fixed n structure, whether there is a unique interior.
That's right. Yeah.
Okay.
Right, yeah.
Thank you.
Okay, I think in order to give us a 5-minute break, we delay all further questions to after the next talk. And thank the speaker again. Thank you.
Thank you.
Okay, let's continue with our online talk. Thanks, Christina Sormani, for joining us online here. So Christina from CUNY in New York, she will speak about introducing various notions of distances between space-times. Please, Christina.
Thank you very much for the opportunity to speak, and especially to speak online. I'm not able to travel for health reasons, so I very much appreciate this opportunity. My co-author on this talk is Anna Sakovic, so I asked if maybe she can help She's in person, so she can help a little bit, maybe write a couple things on a blackboard or answer some questions if I don't hear them. So let me just first give a very quick introduction to the idea. Some of you may have seen this first few slides before, but the rest is different. When we model the Big Bang theory, the Big Bang using an FLRW space-time, that's used often to understand the universe and how it emanates from a Big Bang. Or if you look at the neighborhood of a black hole using a Schwarzschild space-time, or a planet using Schwarzschild space-time outside of a radius, or an isolated empty region, and you model it with Minkowski space, in all of these cases, you're taking a very homogeneous view of the world. And in doing so, you've ignored all the black holes, the dust, the gravity wells in the universe. You've ignored the stars near the black hole. So here, maybe some stars near black holes. And you've ignored the possible black holes and planets of small mass in an empty region. So in these situations, they have run numerics and they know how to run numerical solutions for these, but they actually don't have notions of a distance or how much error there is between the numerical and the idealized solutions. So these models are approximating reality, and they can be run numerically, but they're not smooth approximations. The black holes are not even diffeomorphic, so there'll be all these holes cut out. When you don't look at the insides of black holes when you approximate, you actually cut out that whole tube. So this is a time direction, so a black hole would be a sphere across time. So it moves up in the time direction. These gravity wells around planets could have very strongly distorted metric tensors. So the challenge is to find a distance between space-times that are not diffeomorphic. So we want to move beyond C0 approximations or CK approximations and start studying this in a more geometric way. I want to give another example of people working with Einstein equations, since this was mentioned yesterday. Choquet-Bruhat and Garrosh proved that if you can solve Einstein's equations given some initial data set, this is actually from Choquet-Bruhat's first work first. This initial data set is a Riemannian manifold with an extra tensor, and then you can find a unique maximal future development, which is a space-time, and I'm going to just go forward in time, so I put a little plus. This is a development into the future. If this was your initial time, how the universe looked, and you evolve forward into the future using Einstein's equations or Einstein-Maxwell, or you could have dust, you could have all many different PDEs. There's been shown to be this unique maximal future development. The uniqueness and this maximalness is the Garrosh, the part where they did together. The main idea is that this is basically a partial differential equations problem with an initial data and then a solution forward in time. An example of this would be Riemannian Schwarzschild space, which I kind of drew here in dark blue. And then it's evolves to future Schwarzschild space-time in a vacuum. So that's solving vacuum Einstein equations. So it evolves to future Schwarzschild space-time. Now, there are many, many stability theorems, and I cannot credit everybody for them, using methods from analysis where you're given the initial data converging to some nice initial data. So, for example, it could be close to Euclidean space, or with a cap equals 0, or close to Schwarzschild with cap equals 0. Then the future developments converge to the future development of the limit. So the idea is these stability theorems always have to require a lot of strength in the convergence because they're using methods from analysis. And what we would like to do is prove stability theorems where the manifolds are not assumed to be diffeomorphic. So you might have a very, very small mass black hole, and you want to say, oh, well, that's almost the same as Minkowski flat space-time. So in what sense would these converge? So you need a notion of comparing or defining convergence of space-times when you don't have the diffeomorphisms that allow you to just talk about Gj converging to G0 in some CK sense or C2 sense or W12 sense or whatever sense you're going to study the convergence of the tensors. So instead, we want a geometric approach. So there are intrinsic distances between Riemannian manifolds, which are not diffeomorphic, and that's what we would like to imitate. So this started with Gromov Hausdorff distance. There's also the metric measure distance, and there's intrinsic flat distance. So all three of these are intrinsic distances. They allow you to measure two different spaces and compare them, even though they're distinct spaces and they're not lying within a common extrinsic space. So that's why they're called intrinsic. They're not lying together inside a common extrinsic space, but instead they are separate intrinsic identities. In fact, Gromov called his Hausdorff distance the intrinsic Hausdorff distance. So every one of these intrinsic distances convert a Riemannian manifold into a metric space. So G is the metric tensor of the Riemannian manifold, and it converts into a metric space with a distance d sub G using the Riemannian metric tensor G. And these are all definite notions because, for example, for the Gromov-Hausdorff, the Gromov-Hausdorff distance between two of them equal to 0 if and only if M1 is isometric to M2. This Riemannian isometry, which says that the push forward of the metric tensor on M1 pushes forward to the metric tensor on M2, is if and only if there is a distance preserving bijection between M1 and M2. So the distance preserved here, the distances matching, agrees with the push forward of the metric tensor. The challenge is to convert spacetimes into metric spaces so that we can use these Gromov-Hausdorff metric measure and intrinsic flat distances. So let's talk a little bit about how these Riemannian manifolds are converted. They are converted using this dg. The distance, depending on the metric tensor, is the infimum of lengths defined using the metric tensor between 2 points. And you take the infimum of all these lengths. And g is positive definite on a Riemannian manifold, so the length of g is positive. Then f from M1 to M2 is distance preserving if these two distances agree for every p and q. And you have a distance preserving bijections are, in fact, Riemannian isometries. Spacetimes, so let's scroll up and talk about spacetimes. Spacetimes have Lorentzian metric tensors. So the GVV is less than or equal to 0 when V is a causal vector. So it's not positive definite any longer. In fact, it's a minus plus 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 signature. And so we have these cones. And inside the cones are the time-likes, and including the outside edge of the cones are the causal vectors. And then we also have space-like vectors that point sideways here. Space-times are not just Lorentzian manifolds, they also have a time orientation. So each cone has a future and a past, and this continuously evolves. We write J plus of P for the causal future of P, which is all the Q's, where there is a future-directed causal curve from P to Q. So this future-directed causal curve has each of these cones, and it always is causal. Its derivative is causal at every single point. Future-directed causal. There's a J minus also for the causal past. The Lorentz distance between points that are causally related is defined. So this distance is the sup of the lengths, the Lorentz lengths. And this works fine because you can take the absolute value of G before you take the half power and integrate. But it only works between causally related points. Lorentzian isometries, F star G1 and G2, they preserve this causal structure and they preserve this Lorentz distance. But this Lorentz distance is not defining a metric space because it's not defined between every pair of points. It's only defined between the causally related points. So we ask how to convert a space-time into a metric space. Now we want a distance between every pair of points, the causally related ones and the ones that are not causally related. So we will use the null distance that I defined with Carlos Vega. It's called d hat tau. And tau is the cosmological time of Anderson, Galloway, Howard. So let's just review what is the cosmological time. So Anderson, Galloway, and Howard define this, and there's a related notion by Wald and Yip. Tau, depending on G, is the sup of the distance, the Lorentz distance, from P to Q. You start at P, from point P, and then you're looking at the sup of the Lorentz distance to all Q's in its past. So you go through all the possible Q's in its past and find the sup, the longest possible distance. And this is a value between 0 and infinity, including infinity. Now, if it's a Big Bang space-time, you end up with a finite answer. There will actually be time doesn't go past infinity. And so you can actually get a finite answer here. Anderson, Galloway, and Howard call this regular if it's finite valued, and if when you go along these past inextensible curves that go past but don't go any further, they stop because they reach the edge of the universe, the limit as s goes to 0 along such curves is equal to 0. So it's saying that there aren't extra holes in the space. These were discussed yesterday a bit. Future development spacetimes that we've already talked about that start with initial data also have regular tau. So the Big Bang ones have them, and the future developed ones have them. So these are nice cases where they're regular taus, and so they're finite valued cosmological times in these two settings that we're interested in. Now, in general, like Minkowski space as a whole, or Schwarzschild space as a whole, going all the way back to past infinity, past negative infinity, those don't have bounded cosmological times, but these ones that start from a Big Bang or start from initial data do. Okay. Now, Anderson, Galloway, and Howard also proved that if it's regular, then every point in the manifold has this red geodesic here, these red geodesics going to the initial time. So the initial time is not actually in the space. They're going back to the initial time, starting open 0 to tau at p, such that tau at every point in this geodesic is equal to the time. So these are efficient geodesics going back to the beginning, and they are very useful for proving properties of spaces. Now, n d hat tau, so n is our space-time. D hat tau is this null distance, and we're going to define it here. So this is the definition of our null distance. This is the definition here. It's a metric space when tau is regular. And the way it's defined is d hat tau from p to q is the infimum of these sums. So this is similar to like a rectifiable length, but instead of taking lengths, we take differences in tau. So what we do is we take piecewise causal paths that go back and forward in time between p and q and take the change in the tau as we go back and forth. And this defines a metric space when tau is regular. So that's a theorem in the Somani-Vega original paper. The infimum is over all these collection of points going back and forth where we go future then past, then future then past, then future then past, causal steps. Now, if Q is just in the future of P, we don't need multiple steps and we just get the difference in tau. So when it's actually in the future, if Q is in the future of P, d hat tau is actually going to equal just tau at Q minus tau at P. Okay, once we have metric spaces, so once we convert something into a metric space, we can use intrinsic distances like d Gromov-Hausdorff, dmm, and df. So let me just remind you, what is the Gromov-Hausdorff distance? The Gromov-Hausdorff distance between two metric spaces is the infimum of the Hausdorff distance between images of the metric spaces. And we're taking an infimum over all compact metric spaces Z, and we put the M1 and M2 into Z using distance preserving maps. So these don't distort distances. Z is a metric space, so we have a notion of distance on both sides of this map. And then once we're in the common metric space Z, and we've taken infimum over all possible phi 1s, all possible phi 2s, and all possible Zs. Once we've done this, then recall that the Hausdorff distance between these guys is the infimum of all radii such that U1 is in the tubular neighborhood of U2, and U2 is in the tubular neighborhood of U1. So they're just sort of measuring how close they are in a distance kind of sense. Now, there were also a metric measure, and for the metric measure, you would use, say, the Wasserstein distance instead of the Hausdorff distance, and a mass transport of measures between the two. And the intrinsic flat distance says, oh, push forward current structures and take like the Federer-Fleming flat distance between them, using Ambrosio-Kirchheim theory. So all three of these are notions that involve distance-preserving maps into a common Z. One example of distance-preserving maps into a common Z are Kuratowski maps, and Z could be L infinity space. And that's used a lot in the intrinsic flat convergence, for example. All right, so it seems like this depends on the extrinsic z, and it does, so that wouldn't be an intrinsic distance, but we're taking in femums over all possible z's, and that is why Gromov-Hausdorff is intrinsic. It doesn't depend on the particular z because we're taking in femum over all possible z's. Okay, these intrinsic distances are definite. All three of them are definite. The Gromov-Hausdorff distance equals 0 if and only if there's a distance-preserving bijection f from M1 to M2. And this is actually achieved by first getting almost distance-preserving maps between them by going over here, finding closest points and going back, and then doing the opposite and getting almost distance-preserving, or almost inverting each other maps. And then you take a limit, because these guys are compact, you take a limit of these maps as epsilon goes to 0 if you have actually equal to 0. And this gives you the distance-preserving bijection. And when the MJ DGJs are Riemannian, this happens if and only if f star g1 equals g2. All right, but we're going to talk about spacetimes. So the challenge is the distance-preserving bijections for spacetimes do not give the push forward to the Lorentzian metric is the Lorentzian metric on the other space. So distance preserving using the null distance is not enough. And there are counterexamples in my paper with Sakovich. So these are examples of spacetimes that exist with distance preserving bijections that are not Lorentzian isometries. F star G1 is not equal to G2. The key thing to keep in mind is that Lorentzian isometries preserve the causal structure. You want to know that if f of p is in the future of f of q, if and only if p is in the causal future of q. So recall that the null distance d hat g from p to q is this infimum of these piecewise passed things. And now there's a new definition. The null distance encodes causality if p is in the future of q, if and only if tau pq, the distance between p and q, is equal to tau of p minus tau of q. In other words, if it's shaped kind of like a cylinder, the balls are shaped kind of like cylinders. We already know that if p is in the future, causal future of q, this implies this. That's always true, because we can take just one step. But if it's an if and only if, then we really get an understanding of causality coming from d hat tau and from tau, the cosmological time. So in joint work with Sakovich in a previous paper, we proved that if tau j is a regular cosmological time and it's proper on nj, then d hat tau j encodes causality. Proper means the regions between the level sets are precompact. And then we proved that if f from n1 to n2 preserves time, then like this, tau 2 equal tau 1 of p for all p in n1, and preserves the null distance so that the d hat 2 is equal to the d hat 1. This should be a 1. There should be 2 here. 1. For all p1 and p2, then f is a Lorentzian isometry. So once we have the taus preserved and the distance is preserved, once we preserve both, if we're in a setting where null distance is encoding causality, if we're in a setting where we have this equation, then we're actually able to get f as a Lorentzian isometry between the two. So the key thing is now we need to define distances that give preserving time and preserving null distance. We need to capture both of this information. There are more general theorems of Bircher, Garcia, Heveling, and of Galloway of settings where d hat tau encodes causality. So we did the case where we assume tau is regular and proper, and they do more general cases regular, and they don't require proper, and they're able to, some sort of like globally hyperbolic or future. Anyway, various terminology I don't want to define, but they have more general settings when you are able to get the encoding of causality. So in our new paper with Sakovich, we define various notions of definite intrinsic distances between what we call causally null compactifiable spacetimes. Causally null compactifiable spacetimes are spacetimes which have associated compact metric spacetimes using this null distance and the cosmological time function. And the compactifiable part means that the resulting space is compact, and the causally part is that we're requiring that we have this encoding of causality. So you see, causally is the encoding of causality, and the compactifiable means it's actually compact after you convert it and take the metric completion. Okay, so they're pre-compact before. Once we have these causally null compactifiable spacetimes, which we describe a large class of them, we can define intrinsic distances. So an intrinsic distance will be a distance between spacetimes, which is going to equal a distance between the converted spaces, some sort of distance between these converted spaces. Definite means that the intrinsic distance will equal 0 if and only if there is an f which preserves time and preserves null distance. And because of our definition of causally null compactifiable, including encoding causality, this is if and only if f is a Lorentzian isometry. So this is the largest class of spaces for which we can do this conversion back and forth. But we need to define these d distances. I haven't defined them yet. We're going to define many of them. So there are going to be many notions, various notions of d distances, which will end up preserving time and preserving null distance so that we can get this definiteness. So the first step, which is older, is this notion of timeless intrinsic distances that were basically what I introduced with Vega. That was our plan when we introduced the null distance. And they have been studied further by Allen and Bircher and Kunzinger and Sayman. And that's, I put timeless here, TLS. These are ones where you just take the Gromov-Hausdorff distance after you've converted them. And you don't worry about the time at all. You just convert them with the null distance and you look at the Gromov-Hausdorff distance. And these are not definite. They have nice properties that Allen and Bircher discover and talk about in special cases where N1 and N2 are nice, but they are not definite in general. So we have to keep track of the time, and we have to ensure that we're encoding causality. We have to do both. So there's one type of space-time that Vega and I were exploring, but then stopped working, and then because he doesn't have a research position. And then we've put in our new paper the details about it, which is to assume you have Big Bang spacetimes. So these Big Bang spacetimes, they have a single point when you take them, when you do the conversion and you take the metric completion, they have one special Big Bang point at the base. And so you can use the pointed Gromov-Hausdorff distance between these two. And that's a well-known concept that has been studied a lot, where you take their images, but the points are also close. The very specific base points are close, not just Hausdorff distance between the images. In this case, these PJs, these Big Bang points, is this big point down here. And there's a nice property, which is that the cosmological time in this case is actually equal to the null distance to that point. So this is something that Carlos Vega and I noticed. And if you do that, then you end up where this pointed Gromov-Hausdorff distance is exactly what we need. It will actually conserve not only the distances, but also the time, because this has such a nice formula for the time. Another group that we're exploring in our current paper is the future developed spacetimes. Okay, so these are the ones that we drew with the blue part and the light blue part. So the blue part was the initial data, Riemannian manifolds, and the light blue part is the space-time. And so we call these future developed. And we're only looking at future developed ones, nothing past, because the whole idea is we want this cosmological time to have a beginning to it. So this blue side is the beginning of time, ends up being tau equals 0, cosmological time 0 at that, and then initial data. And we define the future developed GH distance between these two guys, which actually ended up being equal to the GH of metric pairs defined by Ahumada, Gomez, and Che. So this is a distance where you take the Hausdorff, you look at maps that take M1 and N2 into a common metric space, but make sure the Hausdorff distance between the images between N1 and 2 and small, plus the Hausdorff distance from the image of M1 and M2 small, so that the blue parts are close to the blue parts and light blue parts are close to light blue parts. And if you do this, we have this nice situation because the the cosmological time in this setting is the infimum of the distance to the initial data. So again, we get cosmological time from distance preserving from this kind of Gromov-Hausdorff type distance, and we end up again with properness. So we'll get properness for this case too. Now, Big Bang and future developed spacetimes with proper tau are two examples of causally null compactifiable spacetimes. And so I would like to talk a little more about causally null compactifiable spacetimes. They have cosmic strips inside them, which are levels between a tau min and a tau max. So time strips, which convert into compact metric spaces. So we're looking between two levels of time, and they encode causality because that's in part of the definition of these spaces. The Big Bang definite proof involves the fact that this pointed distance equals 0 if and only if there's this f from n1 to n2 bar that preserves distances, and f from the one point to the other point agree. I have to fix that. That's not quite right. It's just equal to the second point. And then, so f also preserves time. It encodes causality, and so f star g1 equals g2. And for the future developed definite proof, we have these two are close. There will be an f from n1 to n2 that preserves distances, and f of m1 will equal m2. So f also preserves time. Tau gq is this infimum of distances to the m's inside the n's, and that encodes causality, and we get f star g1 equal g2. We want to do something like this for causally null compactifiable spacetimes in general. But in general, we don't have this trick that we're using. The Big Bang ones have this. Tau is a distance. And the future developed ones, tau is a distance to initial data. Tau is an initial distance to a Big Bang. That's what we're using in these two. So for causally null compactifiable spacetimes, we don't have that tau is any sort of distance yet. So what about asymptotically flat spacetimes and other spacetimes whose tau is not proper? There's important questions. Everyone's interested in asymptotically flat spacetimes. So for such spacetimes, we're going to have to use the more general causally null compactifiable spacetimes. And what we're going to do is we're going to exhaust these spacetimes that are very large, asymptotically flat, with sub-spacetimes. And the sub-spacetimes will have the union of them equal to the whole space, such that each one of them is causally null compactifiable. So that makes sense. You obviously want to exhaust with compact spaces when you're talking about non-compact space. But we need causally null for each one. So ordinarily, when you're exhausting an asymptotically flat space-time, you get these things. That's natural. You can easily define these with larger and larger radiuses and time strips that are wider and wider. You get shapes like this. But these won't necessarily be causally null compactifiable. So in order to get causally null compactifiable ones, we should take the pasts of regions like this, intersected with times. So this pasts, then they end up causally null compactifiable by Galloway's causality theorem. So now we have a way to exhaust space-times using these causally null compactifiable space-times. And we need then to define distances between causally null compactifiable space-times in general. So the challenge is define a definite intrinsic distance between any pair of causally null compactifiable spacetimes so that we can study these more general spaces. So in the joint work with Sakovich and Spani, we define the intrinsic timed Hausdorff distance, DSTH, between causally null compactifiable spacetimes. And this is how we define it. We take our two spacetimes and we convert them, because they're causally null compactifiable, into compact metric spaces using the null distance, but we also keep track of the cosmological time. So we turn these into compact timed metric spaces. They're metric spaces that have times on them that are Lipschitz 1. And then we define this timed Hausdorff distance between these two compact timed metric spaces. And the way we define this is we write there's two compact timed metric spaces. That's these two guys, right? We take the infimum of the Hausdorff distance, but not in all z's. In L infinity in particular, between timed Kuratowski images. So what are Kuratowski maps? timed Kuratowski maps is a new concept. We just made them up. Okay, they take a metric space into L infinity, a timed metric space into L infinity, and the first component is time. And the rest of the components are distances to points inside the space, where this collection of points is dense in the metric space. So you might say, where does this come from? The ordinary Gromov-Hausdorff distance does this, can also be written and defined the same way with ordinary Kuratowski maps that don't have the time in the first entry. So it's another way of defining Gromov-Hausdorff distance is to use these Kuratowski maps that don't have time on them. So we just added time as a first component. And the rest of the components are the same idea, countably dense collection of points in XD. X is compact, so it has such dense collections. There are many Kuratowski maps. They depend on your choice of dense collections. We're taking the infimum over all such choices of Kuratowski maps from X1 and from X2 into L infinity. L infinity takes the infimum of the differences in times, differences in the first, second, third, and so on. Our theorem says that the intrinsic timed Hausdorff distance between causally null compactifiable space-times is definite. So this is the main theorem from our paper, is that this is now enabling us to handle situations where time is not related to distance that nicely. It is Lipschitz 1, but it doesn't have that nice relationship that it has in the Big Bang or fully developed times. In future work, we can relate it to the Big Bang and the future developed. They should be very closely related, but we haven't done this yet. So now what I would like to do is talk a little bit more about how we actually get this proven, this definiteness. So the first thing we have is that if we're going to just prove that this tau h part is definite, and then after we prove the tau h is definite, then we'll work on the full thing. Okay. So the proof of tau h is definite is suppose d tau h, this timed Hausdorff distance, is 0. So it's an infimum. So that means for all epsilon, we have a pair of Kuratowski maps depending on epsilon that go from the xi's, xj's to L infinity, such that this Hausdorff distance between these two images is less than epsilon. That's just by the definition of infimum. So now we have pairs of Kuratowski maps, which is choices of countably dense points. Okay? Now, the Hausdorff distance has this nice property, which is if you have a Hausdorff distance between two things is small, that means that for every point in here, there's a point here nearby, and for every point here, there's a point here nearby. So if you use this property, that means there's an F that goes from the first space to the second space, x1 to x2. There's also a map that goes from the second space to the first space. And these maps have the property that D and L infinity, because that's where this Hausdorff map is in, between the image, the Kuratowski image of the F, and the Kuratowski image of the original point is less than epsilon for all points in x1, and also vice versa for f21. So let's just understand that a little bit. We're saying that every point P in the first space here, I can map it to the second space and then take its Kuratowski image, and that will be close to the Kuratowski image of the point just from here inside L infinity space. This is from the definition of Hausdorff distance. So if you're doing metric measure or intrinsic flat, this step will be different. Those would need new proofs if you want to show those are definite, and that has not yet been done. But we're using a property of Hausdorff distance in order to get this property here. So now let's look at what is dl infinity. dl infinity is saying that the sup of all the terms is less than epsilon. So if we look at the first term of this, well, the first term of the Kuratowski map is time. So that means the time 2 after the image is equal to the time minus the time 1 is small, less than this epsilon. But we also get every one of these other terms is close. Okay, so we also have all these other distance terms are close to less than epsilon. The important point is the time part is less than epsilon, is going to give us the times, and this part is going to control the distances. Now, for ordinary Gromov-Hausdorff convergence, you won't have this time part, but you will have this part. for ordinary Kuratowski maps without time. Okay, this first part is saying that F1 epsilon is epsilon almost time preserving. That's actually the definition of epsilon almost time preserving. Very close, the times are very close. It's almost as if they're equal, but they're only less than epsilon. And this part, you can do some work to show it shows it's epsilon almost distance preserving. So this proof takes a little bit of work, but it is the same as Gromov's proofs, this part. And the same is true for F2, which is the one that goes back from x2 to x1. And these are also two epsilon almost inverses of each other, meaning that F1 following F2 gives you a point that's within 2 epsilon from its original point. So it's not exactly an inverse, but they're almost inverses. If we take epsilon to 0, then we'll get a subsequence. Now let's think about these. These guys are epsilon almost time preserving, epsilon almost distance preserving on compact metric spaces with compact images. So then Arzello-Scoli, there's an adaptation of Arzello-Scoli used in defining Gromov-Hausdorff convergence and showing Gromov-Hausdorff distance is definite. That version of Arzello-Scoli can be applied here to get a subsequence F, which is a distance preserving bijection. So they are inverses of each other. And this time part gives the time preserving as well. So now that means that tau dth is definite because we have a function f that takes from the one space to the other that is time and distance preserving bijection. Our goal is to show that the intrinsic time Hausdorff distance between causally null compactifiable spacetimes is definite. So far, we have shown, let's look at the definition again. The intrinsic time Hausdorff distance between causally null compactifiable spacetimes is this after they're converted. And we've just showed that this converted part is definite, and we get a distance preserving, time preserving bijection between these two spaces when this is 0. So now let's see the proof that this guy is definite. It's pretty straightforward. So the space-time timed Hausdorff distance is definite. You're given two space-times, causally null compactifiable space-times, and they have this equal to 0. That's only true if and only if their converted spaces equal 0. That's only true if and only if there is this f that is time and distance preserving bijection between them. But then we go over here and we know that f from n1 to n2 gives f star g1 equal to g2 for the Lorentzian metric tensors. And that's last if and only if is following by the definition of causally null compactifiable, controlling the causal structure. All right, so everything is working very well. We have this definiteness proven. Now, in our paper, introducing various notions of distances between space-times, we introduce these causally null compactifiable space-times. We prove a number of theorems about how to find these space-times, and we prove definiteness for the intrinsic distances described above. Okay, so these ones. We also describe possibly definite intrinsic distances. So these ones are just introduced, but we did not do the whole definitions yet. These are Big Bang intrinsic flat, fully developed flat distances, and timed Kuratowski intrinsic flat distances. These appear in future work with Sakovich. They're based on intrinsic flat distance. So instead of Hausdorff distance, we use flat distances using the work of Sormani Wenger and Ambrosio Kirchheim. The challenge is setting up the integral current structure on these spaces, which means we need a structure of bi-Lipschitz charts, all the stuff needed for geometric measure theory. So we're working with Benjamin Mecco on setting up bi-Lipschitz charts on the spaces that we're interested in. So once we have the current structure, then we can do this and define these distances where we'll take into L infinity in the same kind of way with time Kuratowski maps, but then we have to take the flat distance between the images. And we have to redo the whole definiteness in that setting. We also introduced the possibility of metric measure notions for Big Bang, fully developed, and time Kuratowski versions, timed metric measure distances. And this will appear in future work of Mondino and Perales. They're going to use metric measure spaces, and they have to perhaps use the Wasserstein distance once they're inside L infinity, which measures a kind of mass transport between two spaces. We survey other notions of convergence of spacetimes that do not involve the null distances as well. And the paper closes with conjectures and proposed applications. So I think I would like to end here. Thank you. I know I went too fast, but I think it's best to have lots of time for questions. Thank you very much. I don't hear questions unless you pass around the mic.
Yes, thank you, Christina, for the nice talk. We will pass around the mic. So are there any questions?
Hello, thank you so much for the talk. I guess, well, maybe it's a stupid question, but since you're trying to have like defined spacetimes, convert them to metric spaces for defining the distance between the spacetimes, are you also thinking of having some sort of like Hopf-Rinow, or if it's possible even, but for Lorentzian manifolds?
That would be very interesting. So once we've converted them into a compact metric space, there would be sort of a we should be able to use our Zeller-Scoles and get some of that, but we have not looked at that.
Okay, thank you so much.
Thank you for the suggestion.
There's a comment on that question by Anna.
Yeah, I think there is a work by Annegret Butcher and Leonardo Garcia Hevelink on this. Yeah, so this is like relating completeness to properties of null distance. So, yeah.
Other questions? Gerhard.
Hello, Christina. This is Gerhard. Thank you for the lecture. From a physics point of view, it would be very nice to have also notions of distance between the Newtonian setting and the GR setting. So can you make your concept dependent on the speed of light, c, and let c tend to infinity possibly to get even a concept of distance to Newtonian settings?
Okay, so let's see. If we set the speed of light to infinity, then our J pluses will get wider and wider, right? So I wonder what happens to the null distance in that setting. Definitely, we should check that out.
Yeah, I'm thinking of the approaches, the old approaches of Ehlers and of Carla Zederbaum, studying the Newtonian limit. So I think it would be extremely interesting to see whether your concept of distance, some part of it survives. Yes, you let C tend to.
Yeah, that would be very. We definitely should investigate that. Thank you.
Any further questions? Alessandra?
Hi, Christina. Thank you for your very beautiful talk. You mentioned future development into different direction using intrinsic flat distance or metric measure spaces. So there are some reason to preference one over the other, or why to develop both? What do you think? So
the reason. Oh, maybe I just should take a blank piece of paper here. So in some sense, Gromov-Hausdorff is the easiest to work with. With Gromov-Hausdorff, if you have something like a deep well, and then you have another one with a narrow deep well, and then you take the GH limit, the limit ends up being this strange kind of thing. This is the Riemannian setting. And we expect something similar would happen with the Lorentzian one we're introducing. But if you instead do the intrinsic flat distance or the metric measure, you will actually end up with Euclidean space as the limit. So this was something that was explored quite a bit with, if you look at my paper with Dan Lee, why we would use intrinsic flat works well to make thin gravity wells disappear. I should say allows thin gravity wells to disappear. So it was mentioned yesterday about if you want the mass to go to zero on a sequence, the ADM mass to go to zero, that you might want the so suppose you have ADM mass of a sequence of MJs is going to zero. This implies question mark whether the MJs converge to Euclidean, and in what sense. So in conjecture is that it converges in flat sense, in the intrinsic flat sense. It doesn't converge in Gromov-Hausdorff sense. GH convergence fails, but Dong and Song proved that GH removing sets converges. So they're not actually using a notion of distance. They're saying, oh, we can take some sets out of these MJs. Let's call them KJs. Remove these KJ sets, and then it does converge to Euclidean space. That is removing these wells. So they're removing sets and they get convergence. So a notion that which wouldn't require you to remove sets could be to use flat or MM, and you don't have to remove any sets. No need to remove sets. Because these notions of convergence make small volume things disappear. Does that answer your question?
Yeah, surely a part of it. My question was also the difference between intrinsic flat and MM.
Okay. So the difference between intrinsic flat and MM is so in the flat distance, you take these images, you have two images, and what we're going to measure here, so first you move them over. So we take our two phi's, and this is inside some Z. It's M1, M2. And in the flat distance, we take the infimum of masses. These are masses, not ADM masses, but masses in terms of geometric measure theory. A plus boundary B is the push forward of the one minus the push forward of the other. So this is viewed as currents. So this is measuring sort of like the volume between them, a weighted volume. This is like my B, and the A is this part. So it's sort of like measuring a volume between them. It's a very integration defined notion. So this is using GMT, geometric measure theory, and integration of forms or tuples. And then the metric measure distance, you are doing the infimum with the Wasserstein distance between the push forwards of measures. So this is a Wasserstein distance. You're pushing forward the measures instead of the integration over forms. So this is talking about what is the amount of energy needed to transport this measure from here, this measure here, to this one. So it's about how much Wasserstein, how much energy, like how much work is it going to take to put this pile of garbage over to there? It's optimal transport technique. So one of the big differences is this is oriented, and it's things that it's considering how things act on differential forms of the top dimension. And this Wasserstein distance one is measuring measures and transport. So this is used for RCD spaces and CD spaces. And both of them make thin regions kind of not so important. Thin regions with very little measure in the Wasserstein case, and thin regions with very little integration in the flat case. So this is Ambrosius-Kirchheim style techniques. And this is like Villani-Sturm.
Thank you very much for your answer.
Thank you.
Okay. Are there any further questions? I don't see any more, so let's thank Christina again.
Thank you so much.
Okay, welcome back to the final talk of our morning session. We have Alessandro Carlotto from Trento, and he will speak about non-persistence of strongly isolated singularities and geometric applications.
Okay, so thanks for having me here. It's a great pleasure to be back in Pisa. Also a great pleasure to be back to my alma mater. And it's also quite a pleasure to be in this room where it turns out I gave my first ever mathematical talk on the occasion of the third year colloquio di passaggio d'anno. In fact, there's quite a lot of stories I could tell you about my adventures in this building, because it turns out that one floor up there used to be the office of Signor Papini, with whom I used to negotiate the budget for the parties in my dorm. So I could really give a lecture on the subject, but I think it would be enjoyable, but slightly off topic, so I'll get back to mathematics. Okay, so in some sense, this is a biographical lecture, and the reason is given here. The project I'm gonna tell you about stems from a question posed to me by André Neves in the late morning of September 1st, 2014. And the reason why I know that with certainty is that that was day one of my postdoc. I had just graduated from Stanford and I just moved to London. And so André asked me about certain quite mysterious dimensional phenomena related to the landscape of minimal surfaces in nearly round spheres. I'm going to describe the whole thing in just a second. And what I'm going to report about is essentially a full and to some extent very surprising answer to that question, which is based upon a relatively recent manuscript that is joint work with Yang Li, who is at the University of Chicago, and Jian Wang, who used to be in Chicago and is now at Cornell. Okay, so let me introduce the problem and give some context and motivation. And really the problem stems from very basic differential geometry of submanifolds. So the beginning of the story is here. So as we all know, essentially by ODE uniqueness, on a round two-dimensional sphere, the only closed geodesics are the great circles, okay? So they're extremely rigid. And as you may or may not know, Leustenegg-Schneermann theory was developed to essentially prove multiplicity results for closed geodesics in spheres that are not necessarily round, so Riemannian spheres. And in fact, because of that theory, we know that no matter the metric you choose on a two-dimensional sphere, there's at least 3 closed geodesics, simple closed geodesics. But it turns out that what is more relevant for the present talk is the other bound, namely the result that is attributed to Morse, that there exist nearly round metrics on S2 that support exactly three simple closed geodesics. So the bound provided by the Leustenegg-Schnirelmann theorem is sharp, okay? And to be fair, I try to study the argument by Morse, and I think it's fair to say that it's probably not complete, and one should give some credit to Ballman, as also stated in the textbook by Klingenberg. Now, how about one dimension higher? Okay, so if you go one dimension higher, you don't want to talk about geodesics, you want to talk about closed minimal surfaces in that case. And it turns out that there's a very clear parallel, okay? So the story is that on the one hand, you have a nice rigidity result for the round metric. So it was proven independently by Almgren and Calabi roughly 60 years ago that on a round three-dimensional sphere, any immersed minimal sphere must be totally geodesic. So they must be equatorial. They are as rigid as closed geodesics on a two-dimensional sphere. And again, you know, you have somehow a version of the Leustenegg-Schnirelmann theory for in this context, which has not been developed fully, but for instance, we know that given any metric on S3 with positive Ricci curvature, there exists at least 4 embedded minimal spheres. And it turns out that again, that bound is sharp because there exist indeed nearly round metrics on S3 that support precisely 4 closed minimal spheres. Okay, so now you can imagine how the talk is going to proceed. You know, we like induction, right? So how about dimension 4? And if we just focus on the first half of this slide, you know, the obvious question is, are you know, minimally immersed or minimally embedded hyperspheres rigid in the 4-dimensional sphere? Okay. And that's the famous spherical Bernstein conjecture that was posed by Chern in his ICM address in 1970, that was resolved in the negative in 1983. So in 1983, Xiang proved that on the round 4-dimensional sphere, there exist infinitely many pairwise distinct, pairwise non-congruent, minimal embedded hyperspheres, okay? And it's not very important how they look like. We're going to say more about that in a second. But what is important is that somehow they have a very meaningful variable limit. So if you take the sequence of hyperspheres constructed by Xiang with equivariant methods, their limit is an interesting geometric object, which is what I used to call the Clifford football. That is to say, the spherical suspension of the Clifford torus in S4. Somewhat more explicitly, and we are going to see a cartoon picture in a second, you take the Clifford torus in the standard position in equatorial S3, okay, and then you rescale it in a way to get a stationary varifold in S4 that is smooth everywhere except at the north, at the south pole, where you're going to see a singularity, okay? So I'm going to say more about that, but whenever I say Clifford football, that's what I mean, okay? And so here is the question posed to me by André. Okay, so the question is very simply, what happens for nearly round metric? Okay, so the previous 2 slides were about the logical relation between the behavior at the round metric and the behavior at nearly round metric. So the question here is, essentially, can we perturb the picture I just described? In particular, can we perturb the Clifford football? And somewhat probably, in what is a more direct connection to the previous slide, can we perturb the infinite family of minimal hyperspheres that were obtained by Xiang? Or in other words, is it true or false that if I take any nearly round metric, I'm going to see infinitely many minimal hyperspheres? Okay, that would be somehow breaking this sort of dimensional pattern that I tried to describe. Now, it is very reasonable, especially if you come, say, from symplectic geometry, to expect a positive, an affirmative answer to these questions. And in particular, the program that people were trying to address this question was based on standard or seemingly standard techniques in nonlinear analysis. So in particular, there are fundamentally two steps in the possible program in the direction of an affirmative answer. The first step would be to perturb this sort of singular object, which I call the Clifford football, to to similar objects that for nearly round metrics. And this goes in the direction of a very established field, which is the perturbation of special Lagrangian conifolds. And step number two would rather be the desingularization of any such object by means of a sequence of smooth minimal submanifolds, which goes in the direction of, gluing or desingularization methods that have been widely and successfully applied in the theory of minimal submanifolds. A word of warning is somehow that if you were just to try to answer the second question posed by Nels, something that is not gonna work is to simply perturb these minimal hyperspheres one at a time. Morally speaking, the reason is clear, because when I say perturb one hypersphere at a time, I essentially mean applying the implicit function theorem, or more generally apply the so-called Lyapunov-Schmidt reduction when you have somehow symmetries or when you have killing fields. The point is that somehow the neighborhood of metrics that is provided by applying the implicit function theorem is going to depend on the minimal hypersphere you choose. And somehow it may, and in fact will, indeed shrink to a point as you proceed somehow along the sequence. So this talk is about the persistence or non-persistence of the Xiang hypersphere as an infinite family. And in that direction, you can't just try to answer by perturbing one hypersphere at a time. So this was the program suggested by André, and somehow this talk is about essentially explaining why this program is inevitably doomed to fail and why somehow the answer is completely in the opposite direction. Okay, so essentially there's a main theorem which we obtained, which in a way implies any sort of the answer to any sort of question you may ask on the subject. But to get there, I first need to make sure we're all on the same page. So I'm going to recall some basic terminology. So by what we discussed above, basically what I told you about the fact that this sequence of minimal hyperspheres converges to a singular limit, which I call the Clifford football, it is very natural to somehow embed our discussion in a more general framework. And in particular, we are naturally led to studying stationary variables, which for the purpose of this talk, I just want to consider non-smooth counterparts of classical minimal submanifolds. So we want to think about them as generalized subvarieties that are still critical points of the area function, meaning that they're going to pass the first derivative test. In particular, they have zero mean curvature wherever they are smooth, but they may and will in general have a singular set. Now here there's a fundamental word of warning which I give wherever I give this talk, but it's especially important in Pisa, that we are not talking about area minimizing variables. Okay, so the singular set may be large and appear in low dimension, right? So you may all be familiar with Simon's cones and the corresponding foliation of the complement, and that's all great, but that's somehow a totally different story. Here, I'm just imposing a first order condition on the variables we are talking about, and somehow then the zoo becomes a lot larger and a lot wider. Now, all we need to know essentially about stationary variables at this level of generality is that the monotonistic formula you may have seen for minimal surfaces or minimal submanifolds is still true for stationary variables. And in particular, at each singular point, a stationary variable admits a limit cone, that is to say, a scaling invariant stationary variable that lives in the Euclidean space, which somehow encodes the behavior in a neighborhood of that singular point, okay? which is essentially what you would see with a magnifying glass. The problem, or one problem, being that that cone, for instance, doesn't need to be unique in general. And so, in fact, I can quite rapidly reduce, for the purposes of this project, to a subclass of, so to say, well-behaved stationary variables, which is what we call in the paper MSIs, okay? So what is an MSI? Well, roughly speaking, that's a stationary integral variable with only strongly isolated singularities. What is a strongly isolated singularity? Well, a singularity, say, P in the support of my variable V is called strongly isolated if some tangent cone at the point in question is regular. That is to say, if the link of the cone is a smooth submanifold, okay? And there's multiplicity 1. So if that's the case, by pioneering work of Leon Simon dating back to the mid-80s and based on the Loyasiewicz inequality, it turns out that the tangent cone is actually unique, so that's good news. You can then represent your variable as a normal section over such a limit cone with a definite rate of decay. And third, which is reassuring, actually the singular point in question is topologically isolated. So you're not going to see any other singularities accumulating there, okay? So let's see a picture, which is good enough, even if you got lost in the definition. So let's pretend that my ambient manifold is the board or the screen. Okay, so that's what's gonna play the role of this m-dimensional Riemannian manifold with a metric G and dimension capital N. So inside it, we are gonna look at a stationary variable which we postulate to be of the type I just described, so an MSI of dimension little n. Okay, and the way we wanna think about it is essentially encoded in this drawing. And the piece of notation I need to introduce here is the following. So whenever we have a singular point, let's say this edge here, okay, I'm gonna take my magnifying glass, I'm gonna take the limit cone. So where does this limit cone live? Okay, that's precisely what you see on the right. Okay, so the cone is represented in orange, okay? It lives inside R capital N, okay? And it's gonna intersect the n-1 dimensional Euclidean sphere on a certain object, which we call link, that is postulated to be smooth by the definition of MSI, okay? And whenever we have this picture, okay, it turns out that the link is not only a smooth submanifold, but it's a minimal submanifold, okay? That's a basic fact. Somehow minimality of the cone is the same as minimality of the link. And whenever we do that, we introduce a fundamental invariant for this talk, which is what we call the normalized index of the cone. Now, the normalized index of the cone is, by definition, the Morse index of the link minus the ambient dimension. And by a basic estimate due to Jim Simon, so 1968, this number is always greater or equal than 0. Okay? So that's a fundamental thing to be kept in mind. Okay? So let's maybe record it here. I'm going to try this big chalk. Okay, so whenever we have a singular cone CP, okay, we define the normalized index to be the Morse index of the link minus the ambient dimension, okay, and thereby we get a number that is greater or equal than 0. Okay, so let's see an example. And you can guess this is not a random one. It's precisely the example that the whole story started from. So let's consider inside a 3-dimensional sphere the Clifford torus. You can think about it, if you think about S3 as the unit sphere in R4, the Clifford torus is just the product of 2 circles of the same radius, 1 over square root of 2, okay, which is represented this way. Okay, there's a way somehow to generate a spherical suspension out of it in the 4-dimensional sphere, okay? So that's a stationary subvariety, codimension 1, okay, that is smooth everywhere except at the poles, okay? And that's what I denote here by sigma, and that's an example of an MSI, so a stationary variable with only strongly isolated singularities. So in my notation, the ambient dimension capital N is 4. The dimension of the submanifold is little n equal to 3. The singular set consists of the north and the south pole. And if I blow up at either singularity, it turns out I get the cone over the Clifford torus in R4, okay? In which case, the link is again a Clifford torus, whose Morse index is equal to 5 by a famous estimate due to Urbano. And therefore, with my notation, the normalized index of either cone is equal to 1. What I wish to stress is that this number is not 0 in particular. It's always greater or equal than 0. In this case, it's equal to 1. And the other thing to be kept in mind, which may be completely irrelevant at this point of the talk, but is the reason why we can answer the main question posed by André, is the fact that the three-dimensional volume or area of that object, the Clifford football, is pi cube. It's quite easy to compute this. And the important thing is this inequality. So pi cube is less than twice the area of an equatorial S3 in R4. Okay? So I'm going to record it here. So let's say that this is the cartoon of my Clifford football, which I'm going to call sigma. Okay, so the area of sigma is equal to pi cube, and and what we need to recall is that this is actually less than twice the area of an equatorial S3, this number being 4 pi squared. Okay, let's keep this in mind for future records. Okay, so now what is our main theorem about? Okay, so with this, so to say, background notation, it's quite easy to state it. And I'm going to state it in the greatest possible generality and soon specify to the codimension one case, which is simple. Okay, so the setting is essentially what we just described. So we take a closed, smooth Riemannian manifold, well, let's say a closed, smooth manifold dimension greater or equal than 3. I claim that if you pick a metric at random, so there exists a generic subset in the sense of bare of the space of smooth metrics on M, with the following property, that whenever your background metric is generic, so belongs to this set, any G stationary integral varifold will either be entirely smooth, that's great, or have at least one singular point that is not strongly isolated, so it's not of that type, it's going to be more complicated, or case number 3, have only strongly isolated singular points, all having links with Morse index equal to n, or that is the same, is going to have only strongly isolated singular points such that the normalized index is equal to 0. Now, I'm going to comment and discuss some examples in a second, but what I want to stress, which is good enough for the geometric applications that I'm going to present in this lecture, is the fact that in the codimension 1 case, by basic estimates that are essentially classical now, the third alternative does not exist. It cannot possibly occur. And so what are we saying? Well, we are saying that for any n greater or equal than 2, non-smooth MSIs are only observable at non-generic metrics. So if you want me to be even more concrete, an object like the Clifford football is not generically observable. You are only gonna witness or observe such an object for special choices of the background metric, which in particular implies that no matter how cleverly you set up a perturbation theory, you are never gonna perturb the Clifford football for all nearly round metrics. At most, you can possibly hope to perturb it in well-designed, well-selected directions in a neighborhood of the round metric. Okay? So before going on, let me comment about this third case, which is a little bit annoying and a little bit technical. So I'm saying, well, in the codimension larger than one case, what could happen, in principle at least, is that you do witness, even for non-generic, even for generic choice of the metric, MSIs with strongly isolated singularities all having Morse index equal to n, or cones with normalized index equal to 0. So it turns out that there are indeed potential singularities that have normalized index equal to 0. And in particular, there are those can be grouped into two categories. So if you allow the link to be disconnected, to have more than one connected component, actually we have a full classification. So normalized index equal to 0 is only going to happen if your singular model is a cross in R2n. That is to say, the direct sum of two copies of Rn inside R2n. Okay, so equivalently, in terms of the link, okay, in the case of disconnected link, Morse index equal to 0 happens if and only if the dimension of your submanifold is half of the ambient dimension, and then the link is going to be the disjoint union of exactly two equatorial Sn-1 inside S2n. Okay, so the simplest case would be you take two S1s in equatorial S3, you take the spherical suspension on that, you get essentially two copies of S2 that are going to meet just at the North Pole and the South Pole inside S4. Okay? And in the case when the link is connected, then there are also examples of potential singularities with normalized Morse index equal to 0. And the simplest example is the so-called Veronese embedding of RP2 into S4. That's essentially the image of a classical algebraic map. Okay, it's by no means trivial, but it's possible to prove that this object has Morse index equal to 5 in this case. Okay, and therefore it's going to saturate the bound. Okay, and in particular somehow one can easily design again an MSI out of it by taking its spherical suspension in S5. Okay, and conjecturally, but that's not yet a theorem. Maybe we're close. The same happens also for the other Veronese embeddings corresponding to the other division algebras. So in particular for CP2 embedded in the 7-dimensional sphere and the HP2 embedded in the 13-dimensional sphere. However, the full classification in the case when the link is connected is still open, and seems a pretty hard problem even for surfaces in S4, to be honest. Okay, well, let's say for non-orientable surfaces in S4. Okay, that would be the object of another talk. Now, the link with the previous statement is that we claim that our theorem is actually sharp, meaning that if you take an object in this list, although incomplete, we claim that the singularities you can build out of these models are actually persistent. In particular, you are going to see them for any metric, for any nearly round metric, or if you like, for any metric in a definite neighborhood of the round one. Okay, so we expect all such singularities listed above to be persistent. For instance, considering their, again, spherical suspension in the sphere one dimension higher, we expect to see them for a full neighborhood of the round metric. There's a case, so this is a long and complicated story, but there's a case where it's going to be cheap for me to convince you about this claim, which is indeed the case of the cross. So the case when the link is disconnected. Okay, so let's try to see something about it. So like I said, the previous persistence claim can be easily justified in the case when the singularity is a cross. Okay, so what do I mean here? Well, if D is sufficiently small with respect to capital N, in particular, the condition would be that D is less or equal than the integer part of n over 2, floor n over 2. Okay, it turns out that you can take two disjoint d-dimensional sphere and you can embed them here disjoint. Okay, they are going to look like this. Okay, and then you take the spherical suspension in S capital N, And what you get is an MSI, okay? Now, if the equation, the equality holds true, and only if that, in that case, it turns out that you saturate the index bound. So we are in the regime of a potentially persistent singularity. And I claim actually that must be persistent. Why? Well, this is easy to be proven rigorous, but morally speaking, what you can do is that you are gonna perturb each of the two spheres at a time with the Lyapunov-Schmidt reduction, okay? Each of them is gonna persist, and somehow, since you're gonna get, I don't know, 4 of them, okay? You're gonna get a perturbation of the first one and the perturbation of the second one. I mean, you're gonna, so let me say more precisely. Like I said, we take this embedding, we take the spherical suspension of the object in the n-dimensional sphere, and then we perturb one of the two spheres separately at a time. Each of them as a separate sphere is gonna persist. That's application 0 of geometric Lyapunov-Schmidt reduction. So in particular, you know, somehow you take the persistent copy of the first and the persistent copy of the second by dimensional reason, they are precisely going to reproduce the cross that you see at a round metric, okay? This was said very rapidly, but this is a completely elementary exercise. So like I said, by the implicit function theorem applied to each minimal sphere separately, in fact, possibly by a Lyapunov-Schmidt reduction, if you start, for instance, at the round metric, okay, so in presence of Jacobi fields, one proof persistence of the picture in an open set of metrics, thus justifying the sharpness of our general regularity result. Okay. Okay, now let me set aside the higher codimension case, which again would be the object of a separate lecture, and let me get back to the codimension 1 case. Now, if you got lost, like life is very easy, because in the codimension 1 case, all you need to remember is what you see in this box. So for any n greater or equal than 2, non-smooth MSI are only observable at non-generic metrics. Of course, this already says that there's no way you can perturb the Clifford football. How about the other and more geometric question posed to me by André? Namely, if I take a random or any nearly round metric, will I find infinitely many minimal hyperspheres? Yes or no? And I claim that actually with this machinery, it's not hard to give a final answer to that question. And our geometric application, our main geometric application is the one that I stated here, which provides a strong negative answer to the Neves question. So the statement is as follows. So given any epsilon larger than 0, there exists a neighborhood, well, let's say non-empty neighborhood of the round metric on S4, such that for a generic choice of metric in this neighborhood, the Riemannian manifold S for G shall contain only finitely many closed embedded minima hypersurfaces, not even hyperspheres, hypersurfaces of area less than 4 pi square minus epsilon. So what we prove is a generic finiteness of minimal hypersurfaces, no matter the topology, under a pure area bound. So if you have worked on these things, you may have seen other generic finiteness results, but typically they are proven with, say, some assumption on the area and the Morse index, or some assumption on the area and the topology. Here, I'm placing no assumption at all, except for the area bound. And basically, the way this implies somehow the answer to the question about the persistence of Xiang's hypersphere is precisely the red inequality you see on the board, because it turns out that the limit variable of those hyperspheres is an object of area pi cube, which is less than this threshold. And so in particular, given this generic finiteness result, below this threshold, you get non-persistence of the Xiang hyperspheres, possibly with finitely many exceptions, okay? So it could be that the first few elements persist, which is somehow obvious because you can indeed apply a Lyapunov-Schmidt reduction one at a time, but they're not going to persist as an infinite family, okay? That's the point. And just for the GMT crowd here, given that we are in Pisa, let me really tell you the fundamental GMT theorem, which implies this one. It's this ugly looking statement you see here. I'm going to read it just once and then move on. So the statement is that for every epsilon positive, there exists a neighborhood of the round metric in S4 such that for any metric in this neighborhood, here I'm not saying even generic, every mod 2 cyclic G-stationary integral 3-varifold with total mass less than that threshold has only strongly isolated singularities. But remember that strongly isolated singularities are generically not observable. So in particular, generically, any such varifold is entirely smooth. Okay? So just to give you an idea about how easy it is to derive the geometric corollary from this one, okay, let me just say it in words how the proof is going to work. So you say, well, let's pretend I have below that threshold, I have a sequence of close embedded minimal hypersurfaces. So what do? Well, you take a limit. Okay, you have an area bound. You can take the limit in a sense of varifold. Okay, what do you get? Well, you get a stationary varifold whose area is itself below this threshold because the area function is well behaved, of course, under varifold convergence. Okay, and it turns out that essentially by standard Federer-Fleming theory about the behavior of the boundary operator on currents, the limit of my given sequence of cycles is a mod 2 cyclic integral stationary varifold. But now this statement is saying, well, any such limit object can only have strongly isolated singularities. Therefore, generically it is smooth. Okay, but then a posteriori, my supposedly existing sequence of minimal hypersurfaces has a smooth multiplicity 1 limit. Multiplicity 1, again, because we are below the area, twice the area of the least area of a minimal cycle in S4. Okay, so you have convergence with multiplicity 1. So what do? You get a Jacobi field. But then you apply famous theorem by Brian White that says, well, Jacobi fields are themselves non-generic. And therefore you get a contradiction. Okay? So you see somehow that there is this purely geometric, classical geometric question, which is really resolved by a seemingly abstract result in geometric measure theory. Okay, now before I move on to some very rapid ideas about the proof of the main theorem, let me say that our theorem doesn't really exist in vacuum. So in particular, it's part of a big enterprise by many clever people to understand the generic properties both for minimal surfaces, including as a special case, which I'm not going to discuss, the case of geodesic nets, and for the mean curvature flow. There are really great theorems. We have seen one last week, for instance. But there are two aspects that are quite peculiar, I would say, in our result. The first one is, like I already mentioned, we do not restrict to area minimizing subvarieties. And in particular, the local counterpart of this statement is that the limit cones we work with at the singularities do not need to be stable. And if they're not stable, then you cannot foliate the complement. And so it's really, our paper is a first order analysis, really. And the second thing is that we work in arbitrary dimension and codimension. So some of the things I've been talking about have been understood at an earlier stage in the dimension, well, in the ambient dimension 8 case, which is indeed quite peculiar because somehow a few things had been understood already in the 90s. But our applications, well, not the ones I've discussed today, but other that I'm going to discuss at the next PISA conference, basically have a lot to do with, for instance, the behavior of surfaces in 4-dimensional manifolds. Okay, so we really need the arbitrary codimension. Now, just to make a funny remark, of course, this whole business, in some sense, starts with the pioneering paper by Hart and Simon, which, however, has to do with area minimizing integral currents. So it's a great paper. I love it. It's fundamental, but it has to do with minima of the area function rather than stationary points. Now, on this subject, I cannot resist to tell you a funny story. When I first spoke about this thing, I was in Rome, and our esteemed colleague Felix Schulze couldn't make it to my talk because I arrived a day after, and so I was having breakfast the day after my talk, and he sat in front of me, and said, I've seen your paper on the archive, what did you prove? I said, we proved that, like these isolated singularities are, for stationary integral variable are non-generic. And he said, no, yeah, this is R-Simon. And I said, listen, Felix, R-Simon is about area minimizers. And so he immediately calmed down and started appreciating our paper. Okay, so that's quite some difference. Okay. Well, of course, it's not only about Hart and Simon, but there have been many other fundamental papers. I will cite a few. So certainly our paper has a lot to do with the previous one by my co-authors, Yang Li and Jian Wang. There was a fundamental paper by Edelen on ARMA about finitely many diffeomorphism types of MSIs in 8-dimensional manifolds. And then there was a whole industry in the area minimizing case, so these generic regularity properties and estimating the singular set. So that was Chodos, Ljakumovic, Spolor, Chodos, Mantoulidis, Schulze. Last week we had Chodos, Mantoulidis, Schulze, and Wang. And there's also a somewhat different but related side of the story by a student of Camilo De Lellis, Zhenhuan Liu, on non-smoothable singularities. Very rapidly, I should say that the case of surfaces is also a little bit different, because in the case of surfaces, you can somehow pose the same question from the perspective of the mapping problem. Okay, so you can consider maps from surfaces, say, into 4-dimensional manifold, and then you have, so to say, a whole parametric counterpart of the story. And here, really, I should mention the classical papers by Böhme and Tromba, the work by Moore, and then also a paper by Brian White, which is about 7-8 years old. Okay. Okay, so now in the remaining time, I will very briefly say a few words about the proof of the main theorem. And I'm going to be really impressionistic in many ways. So I said that our paper is about stationary variables, so that's a first order notion, but really, essentially, there's something in common to all of my papers, no matter the topic, which is that I take the second variation of the functional in question. And if you take the second variation of the area function, what do you get? You get the Jacobi operator. Okay? So associated to an MSI, you have a Jacobi operator. And now, the first thing to understand is that, and this, by the way, relates to the first talk this morning, is that somehow, if you have an MSI, right, you have a conically singular behavior. So you can't really look at the Jacobi operator as a mapping between, say, standard Sobolev spaces, but it's quite standard and well understood to introduce a weight. Okay, so you need to prescribe somewhat the behavior at the tips if you want to have, for instance, Fredol properties. And now there are two fundamental remarks to be made in this game. The first one is that not all values of tau are born equal. So there are values of tau for which the functional analytic behavior of your operator is going to change. In particular, somehow the Fredholm index, but more generally the kernel and the co-kernel, they are going to somehow jump as you go through certain values of the parameter tau. And that's the object of the next slide. But there's something probably even more important and more peculiar of this setting, which is that somehow looking at the Jacobi operator at the level of this space is just the wrong thing to do. And basically, the reason for that is quite clear. If I were to take tau positive, so imposing decay of normal sections at the tips, well, somehow I'm restricting to very special deformations of a given MSI. And basically, what you need to do if you, for instance, want to develop a perturbative theory is to allow, for instance, motion of the singular points. So there's no way you can prove any interesting theorem in this field by just looking at this functional space. You need somehow to consider an augmentation of the domain, which allows essentially for local translations of the singular points and a fine transformation of the cones at the singular points. So there's a fundamental foundational problem which has to do with cleverly enlarging the domain. Okay, and this is the topic of the next two slides. So let's start with the problem of so to say jumps in the functional behavior of the Jacobi operator. So if you want to find these special values, the idea is roughly the following. So the special values of tau are born as soon as you look at homogeneous Jacobi fields on the limit cones at any singularity. So in particular, if you try to find homogeneous Jacobi fields by separation of variables, okay, so if you look for factored solution, it turns out that you plug in your ansatz inside the the Jacobi equation, and the radial rates of your homogeneous Jacobi fields are those complex numbers gamma that solve this equation, where lambda j is the jth eigenvalue of the Jacobi operator of the link, which, by the way, is assumed to be a smooth submanifold. Okay, so we solve the quadratic equation, we get this set of numbers, which we collect in something that we call the asymptotic spectrum of the cone. Okay? And in particular, we are going to look at the real parts of the elements of the asymptotic spectrum, which are indeed the values of the parameter tau for which the behavior changes. In particular, let me note, without proof, that there are two real numbers that always belong to gamma of c, namely they are 0 and 1. 0 corresponds essentially to translating a cone in the Euclidean space, so no doubt it's an element of the spectrum, and 1 has rather to do with rotation of the cone that keep the tip fixed, okay? So there's always 0, there's always 1, and for the statement of the next two theorems, basically there's a special element here that I need to define, which is this gamma minus c. The precise definition is not very important, there's a whole story behind it, but the point is that we are going to single out a certain number between 0 and 1, okay? Which is somehow an exceptional value of the parameter tau that has a geometric meaning that is particularly important with respect to what I'm saying, okay? The second remark that I alluded to before is the fact that we really need to extend the domain, the natural domain of the Jacobi operator. And in particular, for the next two statements, the extension is the one I described here. So a normal section, well, for a fixed MSI, okay, sigma, a normal section is called translation-like if what you expect is going to happen. That is to say, in a neighborhood of any singular point, my section is just the normal projection of a fixed vector in the somehow in the normal coordinates that live in the background. Okay, and so I define the augmentation of my standard Sobolev spaces by looking at sections that are just the sum of one in WKP tau, plus possibly a translation-like function or a translation-like section, okay? So equivalently, when tau is positive, okay, you can just take this as a definition that's somewhat simpler. So W hat, so the augmented Sobolev space is just your standard Sobolev space, plus the space of local translations that you can define around each of the singular points, okay? Which can be explicitly described this way, and what you need to observe is that this is a finite dimensional augmentation with dimension given by the product of the ambient dimension capital N times the number of singularities. That's a little linear algebra exercise. Okay, so now with all this notation in place, our main theorem is the direct combination of theorem A and theorem B, which I'm going to state. So theorem A is a magic counting formula that I'm going to read. Okay, so we have our usual setting. We take a closed, smooth, n-dimensional Riemannian manifold, and we take an MSI sigma inside it. And then I'm going to restrict to a certain interval of values of the weight, which has a geometric meaning that I don't quite have time to explain. And I consider my Jacobi operator from the domain extended the way I explained the previous slide to the natural target. This is well defined. And the magic formula is the one you see here, which says, well, this one is a Fredholm operator. That's not surprising, but the Fredholm index is explicitly and precisely given by this formula. So the Fredholm index of this operator is equal to minus the sum over the singular points of the normalized Morse index of the singular cones. So philosophically speaking, what am I saying? Well, if you take a smooth submanifold, then the Jacobi operator is a very honest Schrödinger type operator. Okay, so it's Laplace plus potential. The way I came to this formula was really by thinking the following way. So you can consider somehow deformations that transition from a smooth object to a singular object. And as you go to a singular object, somehow you perturb the natural Fredholm index 0 Schrödinger operator in a way that is completely encoded just by the asymptotic behavior at the singular points. Okay? And the contribution, in particular, of, say, a singularity P is given precisely by the normalized Morse index at the singularity in question. Okay? And what do you notice? So here is the question for the audience. What do you notice about the right-hand side of this equation, or equivalently by the left-hand side of this equation? It's less or equal than 0, okay? Because each of the contribution is less or equal than 0, which is already remarkable in itself. And now, can you guess what's going to happen in theorem B? Well, theorem A has nothing to do with generic behavior. Okay, so this formula is always true. Essentially, there's no assumptions. Theorem B is going to say something about something essentially in the opposite direction about this number for generic metrics. So in particular, the statement is that for a generic choice of the background metric, any MSI is going to have a Fredholm index that is greater or equal than 0. And now some of you are going to be scared because they're going to think, you know, what is this guy doing? Well, the problem is that MSIs don't exist. That's the whole thing, right? So because the two formulas are incompatible, except when they're both equal to 0. And when are they equal to 0? Well, they are equal to 0 when each of these guys is equal to 0, which was indeed the famous exceptional case 3 in the statement. Okay? Okay, so a few words about this theorem B before we all have lunch. So theorem B is quite a long and painful story. So we want to think about it as some sort of global Sarsmail type theorem. In a nutshell, there are two fundamental components, which are first a local version that has to do with the design of certain objects which we call canonical pseudo-neighborhoods that are, I'm going to say a couple more words in a couple of minutes, but they are essentially objects that capture a certain fractal structure in the moduli space. And the second thing is the bridge from local to global, which is a certain countable covering theorem in the spirit of a fundamental tool developed by Edelen in the paper I mentioned a few minutes ago, which in turn builds on the so-called discreteness of the space of possible densities, which in turn has to do with the Loyasiewicz-Simon inequality. So in a way, around a pair of the form G sigma, where G is a metric on M and sigma is an MSI in metric G, I'm going to construct this strange object, which we call canonical pseudo-neighbor, that need, on the one hand, to be small enough for a certain, somehow, local Sarsmail theorem to be true, but on the other hand, large enough to allow for a countable covering theorem. A good picture to be kept in mind, which is somewhat purely conceptual, but it's a good heuristic guide, is the way Brian White proved his famous bumpy metric theorem. So the way Brian proved his bumpy metric theorem was essentially by reducing to a standard application of the infinite dimensional Smail lemma. So more precisely, he was looking at the space of pairs, which is called MK in the slide, the space of pairs given by a metric and the minimal surface in that metric. And he proved that this is actually a Banach manifold that is modeled on CK Riemannian manifolds on the background manifold. And then he proved that the natural projector that you have here on the first factor is a Fredholm index 0 operator. Then, ingredient number 3, he proved that there's a fundamental relation between two seemingly very different Fredholm index 0 operators that are, on the one hand, the differential of the projector, and on the other hand, the Jacobi operator of the corresponding pair. And in particular, he proved that these two numbers are equal, and given that they are both Fredholm index 0, you can have the same equation replacing Kerr by co-Kerr. Okay? As a result of item 2 and 3, then in particular, he proved that a pair, G sigma, is a singular point for the projector pi, if and only if sigma is G degenerate. Okay? So in particular, this way, one can really directly obtain the bumpy metric theorem by the Sard lemma as developed by Smail for infinite dimensional Banach manifolds. So morally speaking, the logical scheme of our proof is similar to this approach, with just a little difference, which is that we are, of course, very far from having a Banach manifold structure. I mean, in our case, you know, we are not considering smooth minimal submanifolds for a given metric, but we are considering MSIs, and MSIs are extremely wild objects a priori, because you can have, for instance, collapsing of singular points, right? You can have as many singularities, and they can behave, they can move in a very wild way. So one way of phrasing our paper, or at least the big section that lies behind the proof of theorem B, is the idea of developing a scheme of this type in a metric space setting. So what are really the fundamental mathematical structure that you need to make this work? And the principle is that really you can go very far from a Banach manifold structure. You need a lot less, provided you are willing to work a lot harder. And just to conclude, for instance, the so-called local version of our own Sard-Smail type theorem is encoded in this statement. Okay, so the idea is that for any pair G sigma, where G is a Riemannian metric on M and sigma is an MSI in MG, we are going to design these objects, which are indeed these pseudo neighborhoods. Okay, they are by no means neighborhoods in the classical sense. In fact, they are compact, and they are obtained by making some strange cuts starting from an actual neighborhood. So you start from a neighborhood, you restrict a lot the motion of singularities, which corresponds to cutting a lot of direction. You end up finding something compact with a property that when you project it on the base, which is this space of CK alpha metrics, you get something which is closed and has empty interior, or equivalently, the complement is going to be open and dense. Now, the reason why the condition of having Fredholm index less than 0 comes into play, because remember that theorem B is about proving that generically index is greater or equal than 0. Okay, the way this condition comes into play is quite heuristically quite simple, because if you have a pair with Fredholm index less than 0, well, in particular, by the definition of Fredholm index, then the Jacobi operator cannot be surjective, because the co-kernel will dominate the kernel. Okay, but then morally speaking, the idea is that the set of pairs for which this property is true lives inside the space of pairs for which that are singular for the projector operator. Okay, if you believe in this equation, which is not quite true in that setting, but is morally true, okay, that's precisely the point. If you take a pair with negative Fredholm index, it must the Jacobi operator is not surjective. Therefore, this guy is not surjective. Therefore, you are at a singular pair for the projector operator. Okay. Now, to make this work, a lot of effort is needed. I will say here just a few magic words. So one aspect which is quite fundamental is the construction of Jacobi fields for pairs. So the idea is that you're going to take a sequence of pairs in your moduli space. They're going to converge somewhere, say to G sigma. And what happens in the limit to the corresponding Jacobi fields? And why is this so hard? Well, because typically MSIs don't have a natural notion of strong convergence. They will only converge, say, C2 lock. Okay, and the enemy to fight is the possible concentration of Jacobi fields at the singular points. Okay, so there's a very sharp analysis to make sure that Jacobi fields are not going to concentrate at the singularities. Another thing is that because of that analysis of the Jacobi fields, these pseudo-canonical neighborhoods that we introduced have a natural stratification, and actually a quantitative stratification. So you can define things like a top stratum, which in turn is the key to an inductive descent for proving theorem B. Okay, and basically by induction, one is reduced to proving essentially the case I equals 0, so the case where the kernel is trivial. In that case, really, somehow theorem B is reduced to a certain transversality lemma between certain objects that have a geometric meaning and naturally come into play in the in the game. Okay, so as you can imagine, the story would be long and to some extent, technical, but I'm essentially over time, so I'm going to stop here. Thank you.
Can you say a little bit where the fractal structure appears in your pseudo domain?
Yeah, so the problem is that somehow, so the point is that if we try to mimic the argument by Brian White, a fundamental point is to prove a local version of the Sarsmail theorem. Now, proving a local version in practice means that you need to define a clever notion of neighborhood of a pair, which makes this true. Now, of course, if you were to take, let's pretend we are in a crazy world where we say, okay, the neighborhood of a pair G sigma is just G sigma. Okay, a priori, if we were in a crazy general topology context, we could do that. Now, that would work. This statement is obviously true, but what's the problem? You don't get a countable covering of the moduli space, which is the key to go from local to global. So the idea is that you need to define neighbors that are small, which means compact, that have a projection with empty interior, but they are big enough to allow for a countable cover of the moduli space. How do you do that in practice? Well, the definition is painful. Okay, so I'm not gonna get into the details. There's, as you see, lots of conditions. Some of them are reasonable. Where do the cuts come into play? Well, the cuts come into play here because I'm saying that an MSI sigma prime is in this neighborhood of an MSI sigma, if and only if, well, these conditions are true, but also there's a bijection between the singular points. Okay, so I'm imposing a lot of unnatural rigidity on the MSIs. Okay, so in a neighborhood of a given MSI, there are only MSIs that have the same number of singularities, and where singularities of sigma prime are close to the corresponding singularities of sigma. And if you think about it from the perspective of the moduli space, what does it mean? You are erasing a lot of stuff.
Further questions? One quick one, please.
Hello. So you said that for generic perturbations of the metric, there is no Clifford football. But could you say that if you perturb in a finite codimension of the metrics, then you can construct a Clifford football?
Yeah. So right. So that's definitely true. Somehow the hard thing which we are working on is really to measure, somehow to do that, to implement that program in the optimal fashion, namely to really single out a necessary and sufficient condition on say H, or on a 0-2 tensor H, such that perturbations are possible for matrix G0 plus H. So for instance, if you were to take very special perturbation, like related to, I don't know, Lie group structures, okay, then for instance, you would have the existence of infinitely many minimal hyperspheres for free. But the point is really somehow to quantify the, so to say, the non-generic, the space where you witness non-generic behavior.
Right, I see. Thank you.
Okay, I guess we can start with the second talk this afternoon. We have Anna Sakovic from Uppsala, and she's talking about mass aspect function for weakly regular asymptotically hyperbolic manifold. Thank you.
Thank you very much for the introduction. And first of all, many thanks to the organizers for the invitation and for this great conference. I have enjoyed this 2 days really a lot. All talks have been amazing, so thank you very much. So this talk is about joint work with Romain Gicot from University of Tours in France, and I will talk about basically mass of asymptotically hyperbolic manifolds. So that's kind of general description, let's say so. So first of all, I will spend some minutes just talking about mass in general. So kind of what is mass, where it comes from, and why we study it. And well, mass is so kind of it's something which came from physics. This is something which physicists discovered, and then well, it has been studied rigorously by mathematicians, and it has had many applications since then outside of physics as well. Well, to begin with, to define mass, we need some kind of background geometry. In this talk, we will have 2 backgrounds, asymptotically. So we will have Euclidean space as a background or hyperbolic space. And so we will have 2 classes of manifolds, asymptotically Euclidean, such that, let's see. Yeah, the metric approach is basically Euclidean metric near infinity, and asymptotically hyperbolic manifolds are defined similarly. So also the metric is supposed to approach hyperbolic metric near infinity. So rigorous definition will be given later. And so in both cases, you can think about mass as some kind of invariant at infinity. That is, it's kind of coordinate independent in some sense, or dependent on the coordinates in a good way. And so this invariant is supposed to tell you apart, supposed to enable you to tell apart your asymptotically hyperbolic or Euclidean manifold and the model space. And so exactly how it happens, this is the positive mass conjecture, which tells us how to do this. So asymptotically Euclidean version says that if you have a complete asymptotically Euclidean manifold, or you could have some kind of black hole boundary as well. So it says that if it has no negative scalar curvature, and then the mass should be non-negative, and the mass is 0 if and only if via isometric to Euclidean space. For asymptotically hyperbolic manifolds, there is a similar version. So here, lower bound for scalar curvature is the scalar curvature of the hyperbolic space. So also mass is non-negative. Mass is 0 if and only if the manifold is isometric to model to hyperbolic space. Right. So this is some kind of, so this is not supposed to be the whole history of positive mass conjecture. This is just some kind of sample of works on positive mass conjecture and related topics, which is just supposed to be there to give an illustration of the fact that this is a very active topics where many new techniques have been introduced recently. So, I mean, of course, the history starts with asymptotically Euclidean manifolds, especially with the work of Shane and Yao, where there, well, I guess we have seen quite some elements of the proof in the Marcos talk, for example. So this is like area minimizing submanifolds are used to prove positive mass theorem, and then this proof was extended to dimensions up to 7, I guess, quite shortly after that. Originally, it was in dimension 3. And then in high dimensions, there have been difficulties because of singularities that the area minimizing hypersurfaces might have. And then Witten got the spinor proof around like in 1981. Then there were, of course, some works in between, but I would like to highlight, for example, Lee Floch's work of 2014, because it's kind of, I guess, one of the very few works made in low regularity and has some parallels with our work too. So it's like defining mass in low regularity and proving positive mass theorem by spinor methods. And recently, we have seen some new techniques which came to the field. For example, the level set methods. I'm sure we will hear a little bit more about them in subsequent talks. But for example, we have this work of Breakazar, Skuri, and Stern, where they use linearly growing harmonic functions. And there is this work of Agostiniani, Mazzieri, and Aronzio, where level sets of green functions and some monotonicity formulas that hold along these level sets are used. There is also this work where mu bubbles, which we have seen in Marco's talk, they used there. And well, with their help, one can kind of allow some negative scalar curvature, and one can allow also for ends which are not just asymptotically Euclidean, but some arbitrary ends. So Lan Xuan Huang, who is in the audience, he wrote a series of beautiful works concerning rigidity. For example, some works with Dan Li. This is like a little bit more general setting of initial data. Alessandro mentioned in his talk this work concerning regularity of area minimizing hypersurfaces. Minimal surfaces. So basically, it's written in this paper. So if you combine the results with some standard arguments, you can go up to dimension 11 in the positive mass theorem. In asymptotically hyperbolic case, the story is a bit more new. So essentially, interest in this class of manifolds kind of emerged when ADS-CFT correspondence was introduced in the late 1990s. So in this first work in this direction by Xiaodong Wang is like very much inspired by this ADS-CFT correspondence. So there the mass is really like some kind of conformal invariant of the boundary, and you use this invariant of the conformal boundary to say something about the inside of the manifold. And so essentially his definition of mass is derived just by kind of following Witten's proof in the asymptotically hyperbolic case and seeing what comes out of it, what you can show is positive. And so there is a work of Kruschel-Herzlich. There is a different definition. Well, in a sense, it's a generalization of Wang's definition, but yeah, they are a bit different. So their definition is more in the spirit of ADM mass. So it looks very much like ADM mass does, and it has been derived by Petr Kruschel and collaborators earlier, like using Hamiltonian formalism. And so also they prove positive mass theorem using spinor methods. And then, also variational methods were used by Anderson, Kai, and Galloway in this setting. However, one needs to impose kind of these methods are very sensitive to asymptotics at infinity, so they need to assume quite a lot about about behavior of the metric near infinity, and they had some kind of assumptions there which were removed in this work of Kruschel, Galloway, Nguyen, and Petz. There is also a very interesting work of Kruschel and Delay, which basically says that you can deform your asymptotically hyperbolic manifold into asymptotically Euclidean initial data. So that all conditions of positive mass theorem are preserved. And so essentially you can then deduce positive mass theorem for asymptotically hyperbolic manifolds from positive mass theorem for asymptotically Euclidean manifolds, as long as the later holds. So there is some restriction on the dimension so far, again. Then again, we have a rigidity result. So what happens in the case of mass 0 by Lan Xuan Huang and her students. And I also have some result which is a bit of a spirit of Kruschel delay, but a bit different. But it's not so important here, I guess. The talk is not about it. And also I wanted to point out this work which came also like 2 weeks ago of Krohnke, Aronzio, and Pinoy. This is so in this work, essentially this method is adapted, Green's function, level sets. But I would like to say this is for a different mass than my talk will be about. So the mass which is used here, it's more similar to ADM mass. So it's more like, it looks like ADM mass plus volume plus renormalized volume. So I mean, this is a bit different, but yeah, of course, still very interesting. Right. So just concluding this overview, I just would like to point out why asymptotically hyperbolic mass is much more difficult to study than the asymptotically Euclidean mass. So you know, if we have seen in, for example, Gerhardt-Huyskin's talk, ADM mass is a number, so there is nothing kind of controversial about it. It's just a number. If you change the chart, it should be the same number. For asymptotically hyperbolic mass, it's more like you will see in the literature, usually it is a vector, the so-called mass vector, or it's some kind of functional. And so one can ask what is the reason for this. So like this one simple explanation is that if you look at, so if you think about this kind of CFT approach or point of view. So the mass should be something which is defined on the conformal infinity. And in the case of hyperbolic space, if you think of the ball model, of course, conformal infinity is very interesting. It's a sphere. You can have many functions there. But in the case of the Euclidean space, if you conformally compactify it, you just add the point. So at the point, you cannot have many interesting functions, just a constant. So so this is why partly part of the reason why ADM mass is so simple in comparison to asymptotically hyperbolic mass. So there is another explanation which kind of has to do with this Hamiltonian formalism and how mass has been derived originally in physics. So kind of in physics, when one derives mass, so one basically thinks of this model manifold as a slice of some model spacetime. And our model manifolds are Rn and Hn, hyperbolic space. So we can put them both in Minkowski. So there is a Minkowski also here sitting as a hyperboloid. And then for physical reasons which have to do with Noether's theorem, so mass is related to those isometries of background spacetime which preserve the model slice and at the same time generate motion in time. And so if you think about what we can do with this Euclidean plane, which is isometry we can apply so that we have translation in time, and it restricts to isometry here. So this is just translated upwards parallelly. So there is like one isometry. In the case of hyperbolic space, one can recall the fact that hyperbolic space is just essentially a unit sphere in Minkowski. And so we have this hyperbolic rotations, which are called boosts, which they will kind of keep this hyperboloid in place. So but it will kind of get rotated. So for example, the circle which I drew, maybe it will look like this. So I mean, there will be some motion in time, but hyperboloid is kept on place. So kind of here we will have n+1 relevant isometries, like translations in time, but then also a boost in the direction of each of the coordinate axes. So kind of rotation involving both space and time. Right. Okay, so now I guess I will go to the overview of the rest of the talk. So, so this is like an overview of what this is about. So, now I will proceed basically, first of all, to give a bit more formal, bit more rigorous overview of this definitions of mass in the asymptotically hyperbolic context, which I have mentioned. So I will start with the definition of Wang. So as I said, it's based on the conformal compactification. And there is something which is called the mass aspect function, which is defined on the conformal infinity, and this is kind of the mass. And this definition, as I said, it's for very restrictive class of asymptotics. So definition of Krushel and Herzlich, as I said, it's more like in the style of the ADM mass, so we'll kind of recognize some terms, at least in the integral. So it applies to very, very general asymptotics. And then there is a definition using Ricci tensor. In a sense, this is just rewriting of this Krushel and Herzlich definition. It is geometrically more appealing because you will have like Ricci tensor, scalar curvature there. So yeah, it looks more geometric. But now kind of what one can say is, of course, like if you look at the mass functional of Krushel and Herzlich, it looks much more general. And if you plug in Banks asymptotics into it, you will recover Banks mass. But still, the definition of Bank has something which this definition doesn't have, and namely, it all happens on the conformal infinity. So it really captures this conformal infinity, whereas in the definition of Krushel and Herzlich, it's kind of lost. And so basically our goal with Roman was to try to reconcile these two approaches. And basically what we defined in the end, so we defined this mass aspect function, which kind of, in the beginning, it was just some term in the expansion of the metric, which appears at the leading order, but we have kind of redefined it in along the lines of the definition of the Krushel and Herzlich. So it will look, it will be a distribution on the sphere at infinity, and the formula is kind of, very much related to this one. So I will discuss how we do this. So this definition is for very general asymptotics and kind of very low regularity. And so first of all, I will kind of discuss how we lower the regularity in the mass functional. And then, basically, after that, we will extend the class of functions, which you traditionally plug into the mass functional. And this will allow us to define mass aspect function as the distribution on the sphere at infinity. And I will talk a little bit about conformal covariance in the end and discuss what would be kind of next things to do with these definitions. So I will start with reviewing the available definitions. So this is just some very necessary preliminaries. So hyperbolic space in this talk, I will use the ball model. So it's just unit ball in Euclidean space. The metric is rescaled by the conformal factor, which approaches 0 near the boundary. So kind of boundary will be pushed to infinity. And then I will use this linear, so this linear space n, so of solutions of this overdetermined equation. So it appears always in the definition of the mass. So functions which are solutions of this equation, they are usually called lapses. And the reason for that is that this equation appears when you look for static solutions of the Einstein equations. And then if you found one, this is really like a lapse of the space-time, of the static space-time. So this equation will usually not have any solutions. On the hyperbolic space, it happens to have quite a few solutions. So they are n+1 functions. It's n+1 dimensional space of solutions, and it's spanned by these functions. It is easier to interpret these functions in the hyperboloidal model. So if you look at this hyperboloidal Minkowski, actually these functions are just restrictions of coordinate functions in Minkowski to this hyperboloid. So they are not very strange. They are very natural functions. Right. So, but yeah. Right. So now we are ready to define, to kind of recall the definition of Krushel and Herzlich. So definition is exactly as in the paper. All asymptotics are the same. So we have a complete Riemannian manifold. Metric is of class C1. It's uniformly equivalent to hyperbolic metric. And we say it's asymptotically hyperbolic, basically, so that the mass will be defined. So this is where all these conditions come from. But yeah, we assume it's kind of it is asymptotic to hyperbolic space in the appropriate sense. There is a diffeomorphism mapping an outside of a compact set in our manifold to an outside of a compact set in hyperbolic space. And then if we compare the metric using this diffeomorphism to the hyperbolic metric, so it happens to be in this weighted Sobolev space, W1 to 1/2. This means that this integral is finite. It's not always easy to convert weights into kind of fall off. So here, this condition is satisfied for all yeah, if this difference is of this order, rho to the power tau, where tau is greater than n over 2. Yeah, and then we will have this integrability condition scalar curvature always in the definitions of mass. So this basically says that, well, this is like a difference between the scalar curvature and the scalar curvature of the hyperbolic space, and we require basically that as long as we multiply it by lapses, so these functions that we saw on the previous slide, we get something integrable, something in L1. Yeah, now mass function is this strange integral, which kind of, it's not clear at all where it comes from. But yeah, it's related to scalar curvature in certain sense, but doesn't look very geometric. So as you can see, it's a flux integral. So we have normal plugged in here, and we integrate. So it's outward unit normal to sphere of radius r, and r goes to 1. So it means like we're approaching the conformal boundary. Right, and yeah, this functional is linear in this correction E, difference between the metric G and the hyperbolic metric, and it's linear in V. So V is again in this space of lapses, n plus 1 dimensional space of lapses. Okay, so yeah, actually, why this is well defined, there will be kind of a sketch of a proof later. And then there is this definition of Shadon-Wang. So this so kind of definition of Krushel-Hertzlich supersedes it. So this is why I defined it before. But yeah, so this is defined for a more restrictive class of asymptotics. So we assume we have asymptotically hyperbolic manifold. So in the sense like it was defined on the previous slide. So in the sense of the Krushel-Hertzlich. And in addition, we require that this difference between the asymptotically hyperbolic metric and hyperbolic metric has this form. So this is like something at order rho to n, and then some high order terms in rho. And this term, which I call E bar, so essentially, yeah, this is some smooth tensor, well, near infinity, which is transverse. So essentially, this just means as well, as long as we plug a radial direction into it, it's 0. So kind of metric will be, so this correction tensor in a block form, basically. So if we compute the order of this correction term, so it's order rho to n. And in Krushel-Hertzlich case, it was rho to tau, where tau was greater than n over 2. So this is, of course, much more restrictive. And I can say also that if you increase this exponent by any epsilon, we get 0 mass. So this is like a borderline case of having non-zero mass. Yeah, so how is it related to Krushel and Hertzlich definition? So, well, or what is the mass in this approach? Well, we can retrieve basically Wang's original definition if you take Krushel and Hertzlich mass functional, and then we plug into it this basis of the space of lapses. And then we will see that the mass is basically it's just encoded in the trace of this tensor E bar. So this trace is called mass aspect function. So I will abbreviate it for M sometimes in this talk. But yeah, we see just the first component of the mass vector is just the integral of the mass aspect function. And then the remaining components, you integrate the mass aspect function against coordinate functions restricted to the sphere. Yeah, so essentially we see in this case, the mass is the mass aspect function because we can recover everything from it. Interesting note is that this mass aspect function is not just some coordinate artifact, but it actually has covariant properties itself. So if we change, for example, our asymptotically hyperbolic chart at infinity by an isometry of hyperbolic space, then the mass aspect function will be conformally transformed. So it kind of transforms nicely under changes of coordinates. So there is a definition which, as I said, it's closely related to the definition of Krushel and Hertzlich, but actually it goes back to work of Ashtekar and Hansen in physics. I don't remember which year it was, but it was a long time ago. But kind of rigorously, yeah, mathematics kind of explanation of all this was given by Hertzlich. And also, he also explained how it's related to there were also some other works. I think it was studied in some other works, but kind of Hertzlich did it in full generality. Yeah, so here we don't use lapses for defining it, but we use conformal Killing vector fields of the hyperbolic space, so they satisfy this condition. But they shouldn't be killing, so this definition, but no killing. And then it turns out that there are as many of such conformal Killing vector fields as lapses, so n+1, and they are related by this formula. So divergence of the conformal Killing vector field is the lapse times -n. Right, so the mass functional then can be written as follows. So we have here this very nice geometric looking tensor. So essentially this is just an Einstein tensor. And this is something you add to have 0 when the metric is hyperbolic. Again, we have a flux integral at infinity. And we plug, as we said, plug in conformal Killing vector fields instead of lapses. Well, and the relation of this functional defined like this is just a constant multiple of Krushel and Herzlich. Mass functional, you just have to take x and v should be kind of related by this formula. So how you prove these two are related? This is just using the Bianchi identity, which tells you that the Einstein tensor is divergence free, and then you integrate it against x, and you apply integration by parts, and so kind of with the help of this relation, you will get Krushel and Herzlich mass functional on the one side and this on the other side. So this is like very simple relation between them. But here you will need to assume a bit more regularity. So there's more. Yes? No, because for mass you have to take all of them, because if you just take one, it's not a geometric object. So it's like you should view it as a vector, but you have plugged in all Killing vector fields. But there is something, there is something which is called balance charts under some conditions, like for example, when positive mass theorem holds, you can boost your mass vector, and then you have only the first component, and the rest of components are 0. So this is kind of where it will be useful, such things. Right. So so now I will talk about our results. So just let me repeat again what we are going to do. So we want to have some kind of definition of mass aspect function, but which applies not just in Wang's very restrictive asymptotics, but in general asymptotics like in Krushel and Herzlich. And so we do it in 2 steps. So first of all, we will define mass function in very low regularity, like this. For this, we will use cutoff functions. I will show how it works. Once we have defined mass functional in low regularity, we, as I said, we will enlarge the class of functions to be plugged in. And this will allow us to define mass aspect as a distribution on the sphere at infinity. I would like to say that there is our paper appeared in February, and there is a work, kind of related work in the asymptotically Euclidean case. So this is just like defining ADM mass in this kind of regularity and showing covariance. So it was done by my current PhD student Benjamin Meko and my former master student Stig Lundgren. So this is also an archive a couple of weeks ago. So they basically can get something more general than Bartnik had. So now we are going. So we start with defining mass function on low regularity, and so let us see what the problem is. So we start. So again, everything is the same as in the definition of Krushel and Herzlich. So we have a complete manifold MG. So the metric is uniformly equivalent to the hyperbolic metric. The difference is in this weighted Sobolev space, the same as we had before. But now we no longer assume that the metric is C1. So in this case, scalar curvature will be still defined in the sense of distributions. So you will see why in a couple of slides. So in principle, what I'm going to talk about could be just kind of defined or proven under some assumptions on this distribution. But for simplicity, I will just assume that scalar curvature, difference between the scalar curvature and the scalar curvature of hyperbolic metric is, same condition as before. So it's integrable when multiplied by lapses. So if you look at the mass functional, if you no longer assume C1, but only this, so we see that we have a problem here in this first terms. Yeah, so they are only locally in L2. And we are integrating on a hypersurface of codimension 1. So this may not be defined at all. So kind of we have this term is not okay. So we need to do something about that. We cannot integrate it on the sphere. Basically, in a sense, what we do is kind of inspired by Dan Lee and Philippe Lefloch's work. So they say, okay, you cannot integrate on the sphere, but you can integrate on the annulus. Annulus is fine. But they use the annulus, which is defined in terms of this coordinate function, kind of coordinate radius r. And we instead use cutoff functions so we can get a bit more general definition in the end. Right. So now kind of we are going to kind of replace these boundary terms using cutoff functions. And let us first define a family of cutoff functions. So family of cutoff functions is very it's very general. The definition doesn't depend on it in the end. So maybe let me just draw a picture. So all you need from this family is that, okay, let this be hyperbolic space. So maybe it's somewhere like the origin, and this is some R here. So, so what we want from these functions is just that they should be compactly supported. They should be 1 on some compact set. And then 0. So this is a function Xk. So this set where Xk is 1, we call it omega k here in the slide. And so this sets where the function is 1 should be increasing to infinity. So I can draw one more function. So this is maybe a Xk plus 1. So it should behave like this. Right, and they should have bounded gradients. Otherwise, we don't need anything else. If you, so this sets, I think I said this, but this sets should be increasing, and their union should be the whole hyperbolic space. Right. So now the replacement is quite easy. So, so what we do in this regularity is that, okay, we cannot use this integral, but what we can use is the integral which looks like this. So it looks pretty much the same. So this term is this expression which is linear in V, and in this correction E, it's exactly the same. But instead of the unit normal to the sphere, we plug in the gradient of the cutoff function from this sequence with the minus because it's decreasing there. And so then because it's 1 on the compact set and compactly supported, so we are integrating on the annulus in the end. So I put HN. Right, and then there is no problem anymore with this 2 terms over here. So everything is well defined. So if scalar curvature satisfies this integrability condition as before, then, it turns out that this integral is well defined. It's not dependent on the choice of the sequence Xk of cutoff functions. Most importantly, when we have the regularity as Kruschel and Herzlich do, then we just recover their mass functional. Right. So maybe just a small sketch of the proof. So essentially, the idea is the same as if you want to prove that Kruschel and Herzlich mass functional is well defined, you will use the same principle. So all this, well, it's the same principle whenever you want to show that some mass is well defined. So you start with the linearization of the scalar curvature. Well, first order Taylor formula. So this is like we linearize near hyperbolic space. So this is scalar curvature of hyperbolic space. These are linear terms. Here we actually see why scalar curvature is a distribution in our setting, because all second order derivatives are conveniently hidden in a divergence. So we can move the derivative away. And then we have some quadratic term. So, well, if you want to prove that, for example, crucial and Hertzlich mass is well defined, you will take the Laps function, integrate this against the Laps function. So these two terms combined and this quadratic term, they have sufficient fall-off. So this gives you something integrable. And this term doesn't have enough fall-off, so you don't really, what you need to do here, you need to basically integrate by parts and use this condition that this function v that you picked is a lapse. So basically, kind of, you will just end up with the mass integral or mass functional in the end after this integration by parts. So the thing is that, well, basically this is a formal adjoint of the linearization of the scalar curvature. So kind of when you move the derivative, you will get only the boundary term left. So to show that this definition using cutoff functions is okay, you do the same thing. You just multiply by cutoff function times v. So exactly the same strategy. You just have to be more careful. You don't want to introduce second derivatives of these cutoff functions, because this is kind of our correspondence to, like, its gradient is our correspondence to the normal. You kind of want to keep it. So this is how it's proven. And now kind of the part which I think is more interesting. So this is actually how we define the mass aspect function. So actually, if one inspects the proof, which I have just summarized, one can see that the mass functional, well, of crucial and Hertzlich, or our more general one, actually it's well defined not only if you pick as v the Laps functions, but you could actually allow for a more general class of functions, and we call them generalized lapses. So they do not satisfy this, but some kind of more general condition. So basically, these generalized lapses, they are solutions of this nice elliptic equation, which is kind of well understood on asymptotically hyperbolic manifolds. So this equation you get if you just compute the trace of this, and then you require that the rest falls off as order of row. So there is some price to pay here. So we need to assume a bit more fall-off from our asymptotically hyperbolic metric. So in dimension 3, there is no additional condition, but in high dimensions, you will need to assume that this weight is greater than n minus 3 over 2. We already assumed that delta is 1/2 in our definition. And so now when we kind of extended this class of lapses in this way, we can actually define mass aspect function as a distribution on the sphere at infinity. So this is a theorem. So it goes as follows. If we take any C2 function on the sphere at infinity, then there is a unique smooth solution of this elliptic equation, which appeared in the definition of this class of generalized lapses. So we solve this equation with this initial condition. So basically, kind of this lapse should, in a sense, should have this given function as prescribed value at infinity at some power. Yeah, and well, the thing is that if we want to solve this, we cannot really rely on any available Fred-Golomb theory because because you will end up in a situation where you cannot apply elliptic regularity because you have like C0 space function C0 on the right. So we instead took a very computational approach. So we essentially kind of obtain representation representation formula for the solution of the hyperbolic space, which you can get there because hyperbolic space is very simple with lots of symmetries. So when you compute this solution, you can check that actually this condition is satisfied, and it means that you obtain this generalized lapse function, as we had on the previous slides. So you, all in all, you get a function which you can plug in into the mass functional. Yeah. So basically now we are ready to define our distribution. So we take any function on in the class C2. At the sphere and infinity, we define this generalized lapse associated to it, and then our mass aspect function, which we will clarify later. This functional at infinity is this distribution at infinity is defined by we computed at V0 by plugging in the associated generalized lapse into the mass functional that we have defined before. And this map turns out to be continuous. So the relation of this distribution to the mass aspect of function of shadow bank is as follows. So basically, if we assume asymptotics of shadow bank, so then we have this mass aspect function, which was the trace of leading order term in the expansion of the metric. Then our distribution works like this. This is just integrating our function that we plug in against the mass aspect function. And if you recall the definition of Wang, so components of the mass vector were also like integrating function 1 against mass aspect function, integrating coordinates functions against mass aspect function. So this is this agrees with the definition of Wang, but way more general. Yeah, so I will briefly also comment on the definition using Ricci tensor. So also we can kind of have it in low regularity, and we can also have mass aspect definition using Ricci tensor. So the definition looks as before. So if you're just interested in mass functional, you will be again, instead of unit normal, you will plug in the gradient of the kind of function from that family that we have discussed. And here we had before conformal killing vector field. But now we have gradient of the lapse instead, gradient of the generalized lapse instead. Lapse, if you want just the mass, or generalized lapse, if you're interested in the mass aspect function. So why we define it like this? So the idea is that so this gradient is not exactly a conformal killing vector field, but it's almost conformal killing vector field. So it will satisfy this conformal killing equation at this order, and this is kind of sufficient for this to be well defined and consistent with everything we have defined before. Right, and last thing, one of the last things that I wanted to talk about is, so now that we have all this masses defined, so how do they depend on the chart at infinity? So ADM mass itself is a coordinate invariant, so definition of crucial, so you can kind of form this mass vector from it, like it was in the definition of Wang, just by plugging this basis of the set of lapses. So this vector kind of behaves nicely with respect to changes of coordinates at infinity. So we want to have all these nice properties here. So basically what we want to ensure, so again, the main challenge here is that we have low regularity. So but yeah, what we want to do and how one proves usually such things. So basically maybe I will draw a picture. So one wants to prove, so it's like two steps here. One step is asymptotic rigidity, and another step is covariance. So asymptotic rigidity is basically about the following questions. I mean, we have, say, our asymptotically hyperbolic manifold MG. So, well, there is our compact set K here. Well, maybe let me put K here. And Kg. And then, say we have two charts at infinity. So this phi 1 and phi 2. So it takes us to hyperbolic space. I realized that I probably will not have much place here. Okay. Yeah, somehow had more space in my notebook. So, yeah, okay. So this is a ball model of our show. So let it be like Euclidean space coordinates are x1 to xn, and this is another Euclidean space coordinates y1 to yn, and we have this hyperbolic space sitting here. So this is our hn minus something k prime 1, and this is hn. Yeah, so basically, say we have asymptotically hyperbolic manifold, which kind of, it's asymptotically hyperbolic with respect to two different charts. And then the question is, if I compute mass here and mass there, do I give the same number? Because all these notions that we have seen, they depend on the chart. Even the Ricci definition, even though it looks very, very geometric, but when you plug in this conformal Killing vector field, you take it from the chart. So it's dependent on the chart in the end. Basically this splitting here says the following. So first of all, you want to say that this transition here, maybe let's, yeah. So it is kind of should be of the form A times phi 0. So A is an isometry of hyperbolic space, say a boost. And this is something which is asymptotic to identity. So it's usually very convenient to write it in the form like exponential of some vector field xi, which is small. So well, if xi is 0, you just get x, and if xi is small, so you get something near to x. So this is how asymptotic to identity works. So as a first step, you want to get this splitting. So you want to say that if we have two asymptotically hyperbolic charts at infinity, then they differ by this transition map is of this form. And then next step is basically, well, what you want to show is that this something asymptotic to identity doesn't have any effect on the mass. And then how mass transforms is just dictated by this isometry of the hyperbolic space part. And so there is this formula. For example, if you apply it to definition of Krushel and Hertzich, you will see that their mass vector, which has this n+1 components, if you change the coordinates by a boost, it gets also kind of boosted accordingly. Right. So, well, maybe I'll try to sketch the proof, but before I do so, so just some comments on our regularity assumptions, which we need here. Assumptions we cannot go around with W1 to 1/2 still. Well, we at least want to be sure that everything is continuous, or even C0 alpha. So we have this couple of extra conditions here. So, okay, W1P, P greater than N for Sobolev embedding, and this weight delta has to satisfy this condition. So usually we will have like between 1 and N, this is like usual Fred-Golm range for elliptic operator, well, like the one you have seen in the equation. But yeah, we need to put a bit more here. So we need to increase the lower bound to 2. And this is because, I will show you a little bit of a proof later. So we want basically to be able to discern, to distinguish solutions of some of a geometric elliptic equation from some other terms. So this is why this condition is there. And then we have this another condition, delta has to be greater than 3/2. So the reason for that is that, something that we have discovered in earlier work, actually, Sobolev spaces, like the ones I'm using here, they're not very well adapted to asymptotically hyperbolic manifold. So we discovered it before in our paper, quite an old one, on constraint equations. And there we actually, in the end, we did use other spaces, because there you can get a bit more. So we defined something which is called local Sobolev spaces, and we proved Fred-Goldman theorem for them. But somehow here we had to stick with, we decided to stick with Sobolev spaces, usual Sobolev spaces, because this is what you usually do when you discuss the mass. So but yeah, so in principle, if one wants to get rid of this, this is probably, Sobolev spaces are not the right ones to use. So I will sketch the argument quickly, and it is very similar to the one which Partnik used in his paper of 1986. So there he proves this asymptotic rigidity result for asymptotically Euclidean manifold, so it's the result of the same kind, but for asymptotically Euclidean charts. And the smooth version of this argument was there is some paper, conference paper of Herzig of 2005, where the argument is sketched in the asymptotically hyperbolic case, but yeah, everything is assumed to be smooth, so things are much easier, and it's not all details are worked out. It's just a sketch. But as I said, regularity is low in our case, and so in the end, one has to work with integrals and bump functions. Instead of in Herzig setting, you can just integrate along geodesics and so on. So maybe I'll sketch. Still have some time. So basically, the idea of the proof is as follows. I don't know how we will do it. That's a challenge. So so the idea is that here we have this. So on the hyperbolic space, we have these functions which are our generalized our lapses span a basis of the space of lapses. So we have these functions xi over rho. Here we have the same functions. And basically what we can do, we can move these functions up, pull them back to the manifold M. So of course this is not something geometric, but we can define let's see some function. So xi, xa maybe, because so A will be running from 0 to n. So this will be phi 1 composed with sorry, V0 composed with phi 1, VA composed with phi 1, and we can define similar functions here. I will erase this. So YA is VA composed with phi 2. So this is not geometric, but we can actually promote it to something geometric by solving this equation. I almost want to say magic equation after Peter Stock, but yeah, this is. This equation actually, when you work with asymptotically hyperbolic manifolds, somehow pops up everywhere. Like if you do linearization of Yamabe equation or static, related static equations as well. So basically we can define function, let's say curvy xa, which asymptotes this coordinate function at infinity, and this function is supposed to solve this equation, Laplace G. Xa is. So it solves our this equation basically, which is you have seen it before today. And then we can do the same thing here, but just with YAs. Curvy YA. So this is should asymptote this YA coordinate functions basically, and it should solve Laplace G y a is equal to n y A. So, in a sense, you can think of these functions, xa here and ya here as if, like, okay, you have embedded this asymptotically hyperbolic manifold into some asymptotically Euclidean space, and these are like restrictions of coordinates in this asymptotically Minkowskian space to your manifold. But yeah, to be more precise, I mean, if you look at solutions of this equation, and you impose an additional condition, which is like the one we had in the definition of generalized lapses. So there was this condition that Hessian should satisfy some certain fall-off towards V times B. So if you impose a stronger condition here, you actually get an n+1 dimensional space of solutions of this equation. So it will be like n+1 dimensional solution of equations here. Well, but this is the same equation, so you just got basically two bases of the of the space of solutions of this equation, and then well, you just check how they are related, and then you recover this A. So you may think this A is some kind of a boost of your asymptotically Minkowskian spacetime where this thing sits. Yeah, and then after you have split it this part away, then it's some work to show that this is an asymptotic isometry, but this works too. Right, and basically after you have did this, so this part is asymptotic rigidity, so like showing how two asymptotically hyperbolic charts at infinity are related. So then you just prove, showing how the boost affects the mass is like an easy matter. It's kind of more complicated to show how this asymptotic to identity thing affects the mass. This is essentially just, I mean, in low regularity is quite some work, but this is just again a version of something which Bartnik called the curious constellation in his 1986 paper. So this is like when you compute the mass into different charts, say asymptotically Euclidean charts, and you look at their difference, so you don't really see any constellations, and you still have terms at like very high, like at the order, which is not good. But then somehow magically these terms combine into some divergence, which you can integrate away. And there is something similar here, of course. So if you have our mass functionals here, I emphasize the dependence on E, which in turn depends on the chart. So E is, again, the difference between the metric and hyperbolic metric in the given chart. And so if you have two charts at infinity and we compute these differences and the difference between mass functionals, then actually it turns out that, well, this is this kind of curious constellation. You see that your mass functional looks now like if you have plugged in this Lie derivative here. And then, because these functions, cutoff functions, they are compactly supported, so you will get divergence of something which is compactly supported on ICHN. So yeah, you get a zero here. And then, well, mass functionals are the same if charts are related by asymptotic isometry. So something about what to do with all these definitions. Well, of course, one would be willing to prove positive mass theorem for this, but I think that this part is really challenging. So, like, this is always the case. I mean, positive mass theorem positivity you can prove by you can approximate your manifold by something very nice, something very regular. So. And mass is kind of continuous with respect to the metric, as long as it's well defined. So positivity is not a problem, but rigidity, you really, I don't know what one can do with this. So kind of a naive idea would be, so there is this renormalized Ricci flow, which people have been studying in this setting. So you kind of flow the metric not by Ricci flow, but Ricci minus, plus n minus 1 times the hyperbolic metric, so that kind of you preserve asymptotics and so on. This flow was studied, for example, by Eric Vulgar, Eric Bayot, and some other people, and it's known that The mass actually has, so there is a formula for the mass there, and actually mass is exponentially increasing if it's non-zero. So it's like masses will be scaled by exponential factor of time. But if mass is zero, it will be zero forever. So you can, if you have zero mass and you want to prove that we have hyperbolic space in this case, even if we have low regularity, maybe one could kind of do this flow for a very short time, and then the mass is still zero, and yeah, but everything has smoothed out. But yeah, I don't know. So I don't think anyone has studied it in this regularity. So definitely no one has done this before. Another goal would be kind of so now we have seen there is this, for example, mass vector, and often people also extract a number from it. You can just take it lengths, then it will be invariant. But then, of course, then you lose some information. And also, presumably, when you prove positive mass theorem, so positive mass theorem for asymptotically hyperbolic manifolds usually says that the mass vector has certain causal character. So it's like future directed time, like or something, or causal. But then again, it feels like some information is still lost, and it would be probably desirable to get some inequalities for this mass aspect function instead. So this would be kind of some other version of positive mass theorem. I can say we got some inequalities for this distribution that I have defined, but close to hyperbolic metric. So far away, we don't know how to do. And yeah, it's far from positive mass theorem still. Yeah, and one more thing to do is, of course, so we have this asymptotically locally hyperbolic manifolds with other conformal infinities than the round sphere. Yeah, one would be tempted to do something for them too, but I mean, there is an obvious difficulty there why such a proof doesn't work, and this difficulty is that this space of lapses, it's one-dimensional in all cases. So, yeah, so, right, so this kind of seems hard, but we are working on it. Okay, so I guess this is the last slide, and yeah, thank you very much.
Are there any questions?
Thanks a lot for the beautiful talk. So the mass aspect function you're getting and the mass functional you're getting out of it, assuming more regularity, maybe less than Wang, but still more than you do. Is this related to Michel's?
Yeah, it's all related.
It's related.
Yeah.
Okay.
Yeah. So I mean, I'm saying crucial Herzlich, but kind of. Actually, we maybe followed a bit more of crucial Herzlich rather than Michel there. But yeah, that's the same idea. Yeah. So for people in the audience who don't know Michel's works, it's more like. So Michel gave this very neat proof of well-definiteness and coordinate invariance of mass just by this kind of looking at this Taylor formula and kind of identifying mass as something which comes from as a boundary term when you integrate this linearization of scalar curvature kind of by parts.
And a follow-up question, the decay assumptions you put, do you think they're related to supertranslation in the ambient Minkowski? So that there's actually a reason beyond the analytic reasons you gave that you have to put those thresholds?
I don't know actually. Yeah, I just know about analytic reasons, but
sure.
not for physical.
Certainly enough.
Yeah.
We can.
I think Roman talked to some physicists about that, but they. Yeah, I can't remember what the answer is.
We can have a look.
Yeah.
Thanks.
Are there any other questions?
So I'm wondering, like, when you say you can define the mass functional among all like a function on the conformal infinity, you denote by little v0, right? Can you explain that a bit more? So instead of just working on exactly static potential of hyperbolic space, you can work with generalized lapse function, which looks like you can somehow specify any Dirichlet's boundary data at conformal infinity, right? And denote by little v0. So, and then you say the mass functional is actually a continuous function among
Yeah,
those
exactly.
So, so I think that's great. I mean, because people define the mass invariance to be these like n+1 numbers, right? But now you have actually a lot of numbers to work on.
Yeah.
Is that the case? So what would be the positivity that you expect in this case?
Oh, it's difficult to say. So, I mean, for a while we tried to prove that distribution is positive. At least near hyperbolic metric, we thought we almost had a proof, but we couldn't close it. And then, yeah, it's not always positive actually, but you should kind of mod out some. I guess it should be up to kernel of some geometric operator. Let's say so.
Definitely,
Yeah.
right.
So there is this work of Peter Kruschel where they kind of can more or less, yeah. They can get something negative there. So
you say like it's probably positive in some like integral sense or something.
Yeah, exactly.
Interesting. Thank you.
From a physics point of view, if you assume that this asymptotically hyperbolic manifold is sort of asymptotic to sort of light-like direction in a Lorentzian manifold, from where an observer from an infinity looks back onto this isolated system, is it correct that somehow we should think of the change in the mass, in this mass aspect function, as being related to the change in speed of the relative speed of the observers near infinity?
I think so.
And
yeah.
So is it true that the change in mass then relates to the change in speed exactly as we expect from special relativity? Can that be made?
Carlo, do you have some comment? You said, yeah.
I guess that's exactly the transformation formula you had, right? You saying that if you have asymptotic coordinate changes that are a boost, essentially, up to lower order terms, then her mass vector changes accordingly. Yeah, maybe you pull up the slide.
Well, you mean yeah, this one. Yeah, but okay. Yeah.
I would interpret the second one as saying exactly that.
Yeah. That's. I mean, you can write up how the vector will change if you plug in all these v0s and v1s and so on. Yeah. Yeah. Well, yes. Yeah. Exactly. Yeah. Sorry, I was a bit too small. Yeah.
Are there any other questions? Well, if not, let's thank Anne again for this beautiful talk.